A very good day to everyone. We will begin now. Honorable Chief Guest, Professor Dr. Hasan Mandal, President of the Scientific and Technological Research Council of Turkey, respected Professor Dr. Rümeysa Kazancıoğlu, Rector of Bezmialem Vakıf University, respected Professor Dr. Mehmet Ziya Doymaz, Director of Beykoz Institute of Life Science and Biotechnology, respected Dr. Gitanjali Yadav, representative of APBioNet, the respected members of the Regional Student Group Turkey, respected principal investigators, colleagues, participants, ladies and gentlemen, a very good day to everyone. I am Nihan Sultan. I am researcher at Bezmialem Vakıf University, Beykoz Institute of Life Science and Biotechnology. I'm working at Molecular Biology Lab with Dr. Metin Rafiki. I will be host for the day. Without further ado, I would like to welcome our co-chair of the 5th International Symposium on Bioinformatics, InSyB2021, Dr. Ayşe Fatıma. Over to you, Dr. Ayşe.
Thank you, Ms. Nihan. A very good welcome to everyone. Honorable Chief Guest, Professor Dr. Hasan Mandal, President of the Scientific and Technological Research Council of Turkey, TUBITAK, respected Professor Dr. Rümeysa Kazancıoğlu, Rector of Bezmialem Vakıf University, Professor Dr. Mehmet Ziya Doymaz, Director of Beykoz Institute of Life Sciences and Biotechnology, BILSAB, representative of APBioNet, esteemed keynote speakers, members of the Regional Student Group Turkey, RSG, principal investigators, colleagues, participants, ladies and gentlemen, merhaba, a very good day to everyone. I am Dr. Ayşe Fatıma, co-chair of the 5th International Symposium on Bioinformatics, or InSyB2021. My co-chair, Ms. Esra Bushra Ashok, and I welcome you all to this 5th edition of the International Symposium on Bioinformatics, or InSyB 2021 in short. In this digital age, computers are helping us to solve almost all problems from healthcare to deep ocean studies. Bioinformatics in particular has revolutionized the way we see not just healthcare, but many other subdomains of life sciences. The extensive use of computers in solving biological problems cannot be emphasized enough. InSyB is one of the flagship events held annually by the Asia Pacific Bioinformatics Network, or APBioNet in short. It aims to bring together highly recognized researchers, students, and industry players and other related groups that are working to promote bioinformatics locally and globally. Every year, people join InSyB to showcase their original research and network with global luminaries. This platform provides opportunities for those who seek to grow, thus injecting new blood into the field. This year was the first time InSyB was being held in Turkey, which bridges the Asia Pacific and Europe. Indonesia, Malaysia, and India being the previous hosts. Keeping up with the first times, we have more than 1,100 participants. 84 abstracts were received for oral and poster presentations, of which 65 will be presented over a course of the next 2 days. Our impressive keynote speaker lineup boasts of personalities that have contributed immensely to the growth of this field. Although we would have loved to have you all in person attend the symposium, but due to the COVID-2 pandemic, we had to make this event virtual. But despite that, I'm honored. I'm deeply honored to receive this overwhelming response to the call that began in October of this year. I will end here by thanking our advisors, Professor Dr. Rümeysa Kazancıoğlu, Rector of Bezmialem Vakıf University, Professor Dr. Mehmet Ziya Doymaz, Director of Beykoz Institute of Life Sciences and Biotechnology, Dr. Muhammad Asif Khan, President APBioNet, my co-chair, Ms. Esra Bushra Ashok, and my team, who have worked day and night attending lectures, exams, excruciating lab work to make this InSyB a reality today. Çok teşekkür ederiz, everyone. We welcome you all again. Enjoy all the talks and have a good day. Thank you so much. Over to you, Nihan.
Thank you, Dr. Ayşe. For our next guest, I would like to invite respected Professor Dr. Mehmet Ziya Doymaz, Director of Beykoz Institute of Life Science and Biotechnology, for his opening speech. Over to you, Professor Doctor.
Thank you, Nihan. I hope you can hear me. Okay.
Yes,
I don't think I will be able to list all of you guys like dear professors and doctors, but I'm just going to say, welcome the guests and everybody. Hello all. I guess good morning, the people who are joining us from Turkey and from Middle East. Good afternoon in the Asian side. And I guess good night, the ones are joining us from the Western Europe and America, because there is probably midnight. Welcome to InSyB 2021. This is the first time it's hosted here in Turkey, and obviously first time in our university and in our institute. And we are glad to be the first one that is basically hosting this, and I hope this will continue in the upcoming years. And we are as an institute on doing research on biology and biotechnology, and in the Anatolian side of Istanbul. It's a part of Bezmi and Vakıf University. It's a research institute. We have about 60 researchers, and basically they studying the biology, the different questions of biology and biotechnology. And with the joining of Asif Khan, now bioinformatics is part of our curriculum, part of our research area, part of our investigations. And we are glad that this has been the case. We have about 50 researchers here at BILSAP, Biotechnology Institute of Life Sciences and Biotechnology. And we are working part of a research arm of the university, actually, Bezmi University. And we are very glad to be part of this bioinformatics symposium. And a year or two ago, we were probably not aware of the bioinformatics this far, but thanks to Asif and his group, and you guys have wonderful group of researchers that we are glad to have you guys here. And also we are glad to host this symposium in Istanbul. And I don't want to insert ourselves too much into the symposium. So I wish you a very successful meeting, a very successful symposium, and we'll be gladly watching you guys and learning more about bioinformatics in the next upcoming years. And again, thank you and welcome to Istanbul and welcome to InSyB 2021. And I'll leave the words to Nihan to you.
Thank you, Dr. Raymaz. Now I would like to invite our respected Professor Dr. Rümeyza Kazancıoğlu, Rector of Bezmi and Vakıf University, to give her opening speech. The floor is yours.
Thank you. Good morning, good afternoon, good evening to all of you who are participating to this meeting from wherever you are. I would also like to welcome you to the 5th International Bioinformatics Symposium, hosted first time in Turkey by our university, Bezmi and Vakıf University. I'm happy to be with you in this program, which is taking place virtually, that helps actually to have very distinguished international participants being with us, though it's virtually. I hope InSyB 2021, which is the most important event of the Asia-Pacific bioinformatics, will be satisfactory for all of you. The theme of this symposium is bioinformatics, back to the fundamentals, and aims to open new horizons for young and senior researchers like myself, with oral presentations, poster presentations, panels with expert speakers. I'm very happy to hear that we will be hearing 65 presentations, either orally or poster presentations, and we will be learning from each other. And I would also like to extend my thanks, special thanks to TUBITAK's president, Professor Dr. Hasan Mandal, because he's going to be one of our keynote speakers, but also he was the source that we have Asif Khan with us because of the TUBITAK 2032 project. And of course, my thanks goes to everyone who has contributed from the start, from the idea of this symposium to the organization, to this day, to all the faculty who's working within the symposium, the participants and our staff who have provided the infrastructure, which will continue for the next 3 days. And I wish you a fruitful symposium and congratulate you on this event. Thank you.
Thank you, our rector. We would like to request you stay on as chairman for our next session. For our next guest, I would like to welcome our honorable chief guest, Professor Dr. Hasan Mandal, President of the Scientific and Technological Research Council of Turkey. So the floor is yours.
Yes, thank you. And it's my honor to introduce the president of TUBITAK, Professor Hasan Mandal, and we're just looking forward to hear from you, please.
Okay, so thank you. Our dear rector of the Bezmi Alem Vakıf University in Istanbul, Turkey. So dear co-chairs, organizers, distinguished researchers. So as the president of the Scientific and Technological Research Council of Turkey, so it's a great pleasure for me to be being here together with this flagship event, with the theme of the bioinformatics, going back to the fundamentals. So in this symposium, so I am sure that we will certainly be valuable contributions in this key field, especially during this pandemic period. Focusing on this theme and with these opening remarks, now I am going to be shared to my presentation, which is entitled on co-creating and succeeding together in bioinformatics to leap forward. So now I'll switch to my presentation. Okay, I guess now you can see my screen. First of all, I should say that I am coming. Once more, thank you very much for as an invitation as one of the keynote speakers. I am a material scientist, so while I am preparing my talk for today, I am also in learning from the type of references which I have been used during the preparation step. Yes, I have been just fine. I'll start with a kind of, I am sure that maybe you have been come across, every year it has been published what are the top research fronts. And this was published in 8th of December, so it's very recent. So in the different type of fields, so what are the top front research areas for the year 2021? So, so you can see in here in different type of fields, but in the case of the biological sciences, so I am sure that it's very relevant for today as well, today and also the next 2 days, 3 days meetings, conference. So the top one of the research fronts has been named on the identification of the pathogens of the COVID-19, but complete genome sequence on analysis of the SARS-CoV-2 and also recognition of the IgG2 receptor. So, which I mean that the type of contributions will be shared during this conference. I think it's quite relevant what the top research areas in a global sense. And within this reference document, there are 110 research fronts within these 11 research areas, and one of them is biological sciences, and also the 61 emerging research fronts. So I got to the more details on this, and moving to the detail of these research fronts, and when we, like me, is a kind of a learner, not coming directly from the field, so I can see that what we are bringing together. So the research fronts on biological sciences, information sciences, and also of course the clinical medicine. When I checked first of all the top 10 research fronts in the biological sciences, so I just wanted to go to the detail. I am sure that you are well aware, but so in here, so you can see the top papers or areas, and also the relevant papers, and also the year of these core papers. And also, I am trying to emphasize, for example, the number 1, which I have been already mentioned, and also the number 10. If you see that, it's also taking on the research on image-based, on the deep learning, on the automatic disease diagnosis. So it is a kind of area that is a very hot topic in global sense. And in here, so this is a kind of a conversion of the bioinformatics with emerging technologies utilizing deep learning. So I think this is a kind of I think maybe a message. So when we are talking about computer science, so it is covering with a much larger extent than the classical one. So utilizing the deep learning can provide the benefits for reducing the diagnosis error in such fields as radiology, pathology, and dermatology. And also I have been, as I said, as a learner, so the bioinformatics defined a discipline, a subdiscipline of the biology and computer science concerned with the acquisition, storage, analysis, and dissemination of the biological data, most often DNA and amino acid sequences. So, and then in this transparency also, how the, this bioinformatics and also the deep learning can help to, in the case of the medical sciences. And in here, in the case of the, the one which I have been shared for the main research fronts, and these are the emergent research fronts. And in here also, we can see some of the topics in here. And also again, so the last one has been mentioned in here, the number 11, so the machine intelligence in peptide therapeutics. So again, I can find relevance in terms of the emerging research fronts, also including the neutralizing antibodies, antiviral drugs, inhibitor discovery, pan-cancer analysis, and the machine intelligence that already involved and can also involve the bioinformatics. Now, when we check in terms of the computer science, I have been just mentioned the research fronts on the biological sciences. Now, as I said, the computer science is an area for bioinformatics. And in here, so we can see the top 10 as a research fronts. So we can see the type of areas with the star one. I am not going to repeat them. I am sure that see. So we can see the computer science area is also, it is, in one side from biological sciences trying to be engaged with the computer science and computer science area engaging with the biological sciences. So the top, 4, 5, 6, and the 9th areas are very relevant, what we are going to be talking during this conference or symposium. And in the case of the clinical side, so either has been COVID-19, cancer, and leukemia. And in here, so the new research fronts on clinical medicine have focused on the various perspectives, including the clinical characteristics and treatment possibilities with COVID-19, cancer immunotherapy, and also leukemia. So for me, it is not even easy to differentiate or identify how it is relevant exactly with the biological science or informatics sciences, just checking the names of these research fronts. But I can assume that there is a relevance starting from the number 1 on the clinical characteristics of the COVID-19 patients. So these are involvement of the bioinformatics. And in here also talking on the emerging research fronts, on the again same perspective of the clinical medicine. So these are all what I am trying to show that it's a very recent publication has been mentioned on how the elements on biological sciences and the computer science and the clinical medicine. And now I'll bring to this point with the UN Sustainable Development Goals on number 7, on the number 3, and health, and also the bioinformatics keyword. So when we see what type of areas in year 2021 is coming together with the health and the bioinformatics. So we can see the most, recognized keywords on the publications, during this year. So the gene expression, gene ontology, protein interaction, polymerized chain reaction, Western blotting, cancer prognosis, and cancer growth. So these are the areas which I can see the relevance. So what I am going to say in here, the field of bioinformatics continues to gain importance and focus on finding solutions to various health problems, and including the advances based on the new generation of the sequence technologies. And in here, so when we are talking on maybe on more on the kind of an omic sciences and technologies, and also we are bringing the diseases requiring the treatment. So when we bring the diagnosis data, omics data, and the health records and the clinical data, so which, in a sense that it bringing the all, not only the kind of a knowledge providers, but the interaction between them also very important, because the type of area which going to be discussed for the next 3 days on the recent developments is only be possible to get a more impact if we can bring the, this 4 areas, in terms of the data. In one side, the omics data, and in the other side, the diagnostic data, and also from health records and the clinical data. And so, and by using this data with the, the big data analysis, either is a kind of a destructive or diagnostic or predictive, or and in a way that so we can able to get a more impact by using all the relevant data and the bringing from the scientific community and also from the clinical medicine side. And also in here, so again, when we are talking about the integration of the data, yes, even when we are talking about the omic data, so there are many of them in terms of the as a subtitle, and as I said, also in the other side, the health services data on the right-hand side. So which means that we are bringing the research institutions, scientists, physicians, the medical students, health sector engineers, and health institutions. So this could be only possible to get the right impact, and also looking for the future challenges that these people and these stakeholders, when they come together and work together, so we will able to have a more better solutions for the future challenges. And even by this way, I have been also joined another meeting during the last weekend on bioinformatics, and we have been talking on the personalized medicine. So this is also kind of a further potential, especially using the data on the topic of the bioinformatics. And in the other side, looking for the DNA sequencing, when we are talking even early 2000, it is a kind of an area that is very, very expensive. But now by using this bioinformatics, so we can see I'm an engineer, so this is a kind of a more slow. It is going much more lower, much more faster than what we are expecting. So which means that this will also increasing the further potential of this area. If we bring all the stakeholders together, this will make the real impact for the future. And in this respect, also I have been mentioned in my title of my contribution when I am saying the co-creation of all the stakeholders work together. So since different type of areas and sectors and profiles coming together. I mean, in one side, okay, life sciences and computer science, but at the meantime, also we are bringing, like me as an engineer, and also social scientists, because this is also make the real impact on this area. And so therefore, when we are increasing the scope of the ecosystem collaboration and also the intensity between them, so we will have a much better solutions in the type of challenges of the for today and also for the future. Yes, now I am from this introduction. I am moving to a kind of a. I am the chairperson of the main funding agency of Turkey for universities, industry, individuals. So how the ecosystem is changing on research and development and innovation ecosystem. So it is in the past, it is used to be a kind of a linear interaction between the knowledge provider and knowledge user. So the knowledge provider and knowledge user between university, industry, university, or university, I mean, all relevant stakeholders. But it is now changing from the linear to type of a reversible, reiterative type of innovation. So which means that, I mean, because the type of knowledge, it is not an easy to understand and to get a better impact. So this type of interaction between the knowledge creator and knowledge user should be reversible. And also, when we are talking about, I mean, I am sure that most of the colleagues are attending this meeting in the field of the relevant technology areas of the bioinformatics, biological sciences, or computer sciences. But also at the meantime, we should be take an importance of the technological solutions in certain, up to certain aspect, yes, definitely is enough. But after certain cases, it's not enough by itself. I can give the, I mean, right example, what we are, I mean, challenging for today, I mean, during this period is the pandemic period. I mean, at least in Turkey, and I am sure that in many parts of the world, so the people now have access to vaccine. But still, the remarkable percentage of the population still don't want to get the vaccine. So, which means that only the technological solutions is not enough. So, also the science and society type of interactions in the scientific way, social science and humanities also it is quite an important fact on the development of the technological solutions. And so therefore, my contribution, so interactions between in the relevant stakeholders or partners of the ecosystem, not only a kind of a collaboration, it's a kind of a co-creation. So the co-creation means that using the same infrastructure, using same human capacity, so sharing the knowledge and get together, and especially during the pandemic, at least in Turkey again, we have been really able to use this type of new way of the collaboration during the pandemic period. And the organization which I am representing, which is TUBITAK, it was founded in 1963. So we have been just celebrated 58th anniversary. And we are the, as I said, main funding agency for universities, industry, human improvement of the human capacity by means of the research fellows, and increasing the science and technology in the society, and also responsible for international collaborations on the STI area. And in the other side, also we are doing the research by means of our 23 research institutes with more than nearly 5,000 research personnel. So you can see what type of areas which we have been involved. and including the Genetic Engineering and Biotechnology Institute, which was very, very active during the pandemic period, especially during the vaccine development area during the pandemic period. And in Turkey, so this is our funding part, philosophy or strategy. And in the left-hand side, so you can see the type of priorities which we put into the front side, and the infectious diseases and the climate change type of actions. So Industry 5.0, not 4 is a 5.0, which means it more human-centric and more sustainable, and also the digitalization. So when I bring the especially for today with the star ones, so the infectious diseases and the digitalization, I mean, exactly matching what you are going to talk during this conference. But as I said, our funding mechanisms, it used to be in the past to create more potentials, but now we are looking forward more impact, and impact on an economical impact, and more on societal impact, and also the national security impact, of course. And so this type of impact could be only created by means of the new knowledge creation, and also the new human resources by co-creation type of funding mechanisms. And in here, I mean, in this, crowded and complicated transparency, I'm not going to the detail, but it's trying to say, I am trying to say in here, so instead of, we are funding the, of course, we are continue to fund the individual small projects for improving the capacity in the country, but also at the meantime, we are giving the much bigger budgets for platforms rather than the projects. And these platforms work together with the creator and knowledge user in the same platform, and it is quite dynamic. And by means of this, we are looking for more than the capacity building, we are looking for the more impact, outcome and impact. And in the right-hand side, in the same manner, we are trying to be introduce different type of programs to also attracting the, researchers to come to Turkey to continue their research, at least for a certain period of time, but also at the meantime, again, to bring in the right partners as a knowledge creator and knowledge user to make the co-creation type of human capacity building. And one of the examples is given in here, the industrial PhD program. And so the type of areas which we have been, especially these big platforms, so the type of areas which you can see in here, of course, the area of bioinformatics is exactly match in this, our strategy. And also you can see type of some of the examples, of the platforms already been existing and working. So, so you can see so many partners come together from university side, from industry side, and the research institutes, they are working. So this type of platforms, either technology development platforms, and in that case is led by the either university or research infrastructure in Turkey, or it's a product development, and in that case, it's coordinated by the company. But again, collaborating with the research institutions. And in all these platforms, we are also inviting to international partners as well to join. So as I said, so these are very dynamic. So it doesn't mean that, when during the, especially running the platform, so the one project can stop and other new projects can be initiated. And also some of the partners leave from the platform, and some of the new partners also can join the platform. And whether this type of action has already been tested, yes, indeed, it has been tested and is working. So one of these platforms has been a kind of a real solution in the pandemic. So we have been formed a COVID-19 Turkey platform, And in this platform, 17 projects come together. So the 7 of them vaccine and the 10 of them drug projects. So it's a kind of what does it mean as a co-creation? So they, especially in the early stage of the pandemic, is a very difficult access to, even if you have a grant, that is difficult to access the infrastructure and consumables, and especially the logistics. So by using the, these 49 research institutions, either universities, state research labs, and also the companies, they come together under the, so Genetic Engineering and Biotechnology Institute. So it is only a coordinator and supplying the infrastructure. And during this period, especially for challenge tests and also the clinical trials, they are all being coordinating. And 436 researchers come together in this platform. And I am also pleased to say that nearly half of them, 213 of them, are the students. So this is also giving a kind of although we are having a challenge, but also we are creating the human capacity for the future as well. And also, we are also using a kind of bioinformatics in terms of when we are working on the repurposing type of drugs. And I guess that one of our colleagues also, Serdar Duda Hoca, will be also attending this meeting and give some of the results during this conference. And yes, so you can see, at least within the 17 projects, 2 of them has been, moved much more fastly. And so you can see one of them is a new type of vaccine, is a virus-like particle type of vaccine. And myself and also the Minister of the Industry and Technology are the volunteers for the phase 1. Okay, so the phase 1, and now it is in hopefully in phase 3. And maybe it is moving maybe rather than slowly what we are expecting, but in terms of the type of potentials, it is giving a kind of a potential, not for today and also the future, in terms of the either COVID-19 or and especially when we are working on the different type of variants. So it is very easy to develop it and adapt it. And also this gives also platform for other type of infections, diseases for the future. So, and also in the right-hand side, also you can see in terms of the kind of medicine is come out by means of the drug repurposing. And as I said, it's already been, I think, going to be mentioned during this conference. And in the other side, as I said, and also one of the conference organizers of this meeting is one of the outstanding research fellows who's doing his research studies in Bezmi Alem Vakıf University. And so this is also kind of a program which we are attracting the researchers to come to Turkey, continue their research. And we are giving at least in Turkish perspective, remarkable, quite well enough research fund mechanism. So, and now we will, within this month, we will announce the second end of the results of the second call, and there will be more researchers will also join to this program. Yes, so within this program, so our researchers around Turkey, so they are doing their contribution, not only doing their own research in terms of well experienced as a researcher, but also they are supervising up to 5 graduate students. So the type of an impact by means of this program, not only the research by the scientist is doing, also we are getting a kind of a contribution during his supervision to graduate students. And some other programs in Turkey, which I am going to be mentioned, also, especially during the pandemic, we have been learned that the researchers in every level. So the every level means including the bachelor students, because under the normal circumstances, so the research more concentrated on the PhD, but during the pandemic, so many young researchers also joined to do this program. And now this is a program which we have been called, this is a STAR program, in Turkish is a researcher scholarship program. And so internal researcher scholarship program. So they are joining PhD bachelor students to the projects funded by TUBITAK. So, and this is a program, I mean, it is maybe strange, but it's created by the students by itself. So this is not a program which we designed. The design came from the students during the pandemic, because they said they want to be joining also the research teams while they want to stay back home. So, and now we have been more than 3,000 undergraduate students now in this project, and we will be fund another 3,000 within early next year. And as I mentioned also, as a kind of a co-creation methodology technique for the human capacity of the PhD students. And in this forum, so it is, I am sure that maybe you have heard many industrial PhD programs, so the university and industry coming together. But the specialty in this case, so the students not funded during the PhD, they are also funded during the employment stage. I think this is one of the, I mean, which we think that is a novelty. So 4 years during the PhD, we are funding them. And after the PhD, next 3 years during the employment stage, up to 60% of the salary is funded by TUBITAK. So this is giving a kind of a motivation for the student and also for the company to be joined to this program. And right now we have been nearly 1,200 PhD students are working in this program, and their projects relevance to the industry. And different type of, I mean, also the programs which we are running either for universities or industry, and also this is the priorities for this year under the, I mean, digitalization in health. I am sure that you can see the type of subtopics that which we are funding for this year. So, and there is quite relevant areas what you are going to discuss during this next three-day event. And also another program is a funding program, again, bringing this knowledge creator and knowledge user, industrial, university industry research funding program. So in this case, the total fund, I mean, 25% of the total fund is paid by the industry and 75% by TUBITAK. And also we have been published a map, competency map of all universities, and also in the 131 fields. And so this is for one of the 131 fields on biochemistry, genetics, and molecular biology. So you can see all the universities in Turkey is a kind of a potential in this area, this subtopic area, and there are another 130 this type of subtopics. And so you can see the universities in terms of quality and also the quantity. So the universities can, I mean, measure their potential and also can make the benchmark. And also this is also kind of a tool that the university and industry coming together. So industry is looking for, I mean, this is the area which I need, so which I can collaborate and ask. So this is a kind of a tool on the basis of the scientific output and also the project-based potentials. And another type of funding mechanism, we are bringing again two companies in this case together. The company has been technology provider, other one is a technology user. So, and also you can see the type of areas also relevant to these topics of the conference. And again, it's a kind of a win-win-win type of model. So the certain amount of the funding is paid by the technology user. Another one is for the by the TUBITAK. So this is again sharing the risks and also the gaining the potentials together with the technology provider and technology user. And another program which we are also again running by means of especially patents coming out from the universities during in a license process to do companies. Up to 75% of the company licenses fee is going to be paid by the company to university, is paid by TUBITAK. So again, this is increasing the interaction between the knowledge creator and knowledge user. And in terms of the internationalization, so you can see that these green areas, which we are all collaborating around the globe with 91 institutions from the 64 countries. And at the moment, nearly 550 international projects are going on. So we are always welcome to work on international projects with the funding agencies in the respective countries. And if not named in here, so we are also open to make more collaborations with the countries are not named in here. And finally, also another big potential for the research environment for the future on bioinformatics, especially on the Horizon Europe program. It's the largest funding program around the globe. For the next 7 years, starting from 2021 to 2027, is nearly 96 billion euro. So it is a huge amount of funding part. And in here, so number one is you can see in health. So you can see the potentials in here as well. And so this could be also, when the end of the, outcomes of this conference could be a kind of a potential to start for a new project under the Horizon Europe. And my final message is to bring all relevant stakeholders in this conference, but I am expecting that, more than improving the capacities, to get the right impact is very important, and the co-creation is the type of right model which I think. And during this next this conference for the next 3 days, I am sure that it is bringing all the relevant partners, and I am sure that we will have kind of results. Also, my institution TUBITAK will get benefit from that for the future course. So in this respect, so my final message is, so we need a future of co-creation to achieve a more sustainable and healthier future. So I thank you very much once more to invitation for this conference. And I also wish that the fruitful and impact-oriented type of contributions during this conference. Thank you very much.
Thank you, Professor Mandal. I appreciate, and I'm sure all the listeners appreciate the talk. And as I guess this is a testament to TUBITAK, which is the lifeline of research in this country, and hope to continue to fund us and hope to continue to help us doing our job. I guess this is Dr. Fatima, this is we are going to move to Professor Gita Yadav now, or I guess. Why I would like to thank Professor Mandal, and I guess I will just end here, and then you take over from here, okay?
Thank you so much, Mr. President. It was really very fruitful listening to you. Could we also make another request to you to declare our symposium open, please?
Okay.
Could we request Dr. Mandal?
Yeah,
to declare the symposium open?
Yeah, I guess that's the Professor Mandal, I guess the organizers would like really the official opening of the symposium declared by you, and I guess that's the message.
Please. Professor, we would just like you to say that to declare the symposium.
I can say that now the conference is formally open. So I wish that very successful and fruitful conference and discussions, interactions, and meetings. And also I am very honored to be joined and to give this privilege to open formally the conference.
Thank you so much. Thank you so much, Professor.
Thank you.
Thank you so much.
Thank you.
Thank you.
Thank you once again, Mr. President. Our next guest is Dr. Gitanjali Yadav. Today, Dr. Yadav is representing Asia Pacific Bioinformatics Network. Dr. Ayşe now will introduce her. Over to you, Dr. Ayşe.
Thank you, Nihan. Thank you so much. Dr. Gitanjali is here with us. To introduce Dr. Gitanjali Yadav is a member of the APBioNet Executive Committee since 2020 and has been taking the lead in the organization's education initiatives. She is currently scientist at NIPGR and a professor at the Department of Data Science, IISER Bhopal. She is an expert in genomics and artificial intelligence with applications in food security and conservation. Dr. Yadav has received several awards, including the Hamid Fellowship from the University of Cambridge, Exceptional Talent Award, and from the Royal Society of London, INSA Medal, and the Sastra Obed Siddiqui Life Sciences Award. Dr. Yadav promotes science in as a way of life to the students in schools and colleges and has been an ambassador for women in science. Thank you. The floor is yours, Dr. Yadav.
Thank you so much, Aisha. A pleasure to have been introduced by you. And it's very, very encouraging for me as a representative of the Asia Pacific Bioinformatics Network to see the flagging off of InSyB 2021. We are delighted to be part of this international symposium in bioinformatics, and all the very best for the next 3 days, and most especially so because this is a flagship event of the Asia Pacific Bioinformatics Network. So I'd like to, share my screen if that is, all right. Can I just?
Of course, you can share.
Just a sec. Yes, it's working. Thank you so much. So as I said, we are delighted to be part of the Asia Pacific, for InSyB to be part of the Asia Pacific Bioinformatics Network as one of our leading flagship events or annually leading flagship events. And this year, particularly, we are very happy that it's been hosted for the first time in Turkey and by the Bezmi-Alem Vakıf University. And due to the SARS-CoV-2 pandemic, as all of you are aware, we have decided to move online with this event, but the focus is on young researchers as ever. And I've been listening to Professor Hasan Mandal and Dr. Mehmet also, and I'm very happy that both of them focus so importantly on impact, particularly co-creation oriented human capacity building, which I think is truly the crux of what Asia Pacific Bioinformatics Network aims to do. And this year, particularly because we are now, all of us are, most of you listening to us today or participating in the InSyB are very well aware that this is the post-genomic era and biological data is growing rapidly. So bioinformatics is the I should say the key that provides the lifeline to manage all of these data, knowledge, and discoveries. And through this symposium, we are hoping very much as Asia Pacific APBioNet that InSyB is going to bring together students, academics, industry players, working together and being able to interact with each other to discuss different aspects of biomedical sciences and healthcare. especially for mixing, cross-pollination of ideas, building collaborations, lasting networks with each other. And it's a great opportunity to exchange ideas from luminaries in the field. So the next 3 days, I'm completely very excited about these 3 days. You've all seen and heard before that the theme of this is bioinformatics going back to the fundamentals. But as you can see, the main tracks are going to be very, very cutting edge: big data, CAD, general biology, and of course, the thing that's preventing us from meeting each other in person, the SARS-CoV-2. So just to give a background of the Asia Pacific Bioinformatics Network itself, we established, I should say we are the oldest 23-year-old community in the Asia Pacific region. We were established in the year 1998, and this was in Hawaii when the Pacific Symposium on Biocomputing was underway, and that's when we were founded. And since then, the idea has been we need to encourage, support, and extend computational biology for translational research, for networking for the entire Asia Pacific region. And our flagship conference is the INCOB, which many of you would already be aware of. I will tell you more about INCOB once I've introduced ourselves. So this is the Asia Pacific Expo. I'm very privileged to be representing the Expo for the last year and a half, particularly during the pandemic, as we have moved into biology students and life sciences students all over the world who have been locked down because of the pandemic. So there's this this rock and roll that we used to be listening to long ago. You get locked down, you get up again, nobody's gonna keep you down, right? So we get locked down, but we come back up, and bioinformatics is the way out, because you can work on your machine, and the digital era allows you to integrate your data with everything else that's available and do data science as never before. So with that, of course, coming back to what I said about our flagship conference, INCOB, the International Conference on Bioinformatics, was the first flagship conference of APBioNet. And you'll be glad to know we've just completed our 20th run of the INCOB last month, and this was hosted in Yunnan, China. Again, it was a hybrid event, mostly virtual for people outside of China. And the current event, INSYB, is a short sister event, but I'm going to show you how it's completely fifth year. So we at APBioNet are an expanding community, as you see, from the 1998 going on here. 5 years ago, the INSYB was instituted, and the whole idea of INSYB was that it would be a short sister event to the INCOB, and its focus would be on thematic discussions targeting younger researchers in the local communities, of regions where we have held the INSYB. And now, only in its fifth year, it's already diversifying so incredibly. It's wonderful for us as APBioNet to see the impact of INSYB, but city building impact. It's really happening live before us as with INSYB as part of APBioNet. And so you probably know that Turkey is held. No APBioNet event has been held in Turkey before, so InSyB 2021 becomes our first connection within Turkey for the APBioNet, and that's fantastic for us. It's also, the APBioNet has also been a very expanding community in terms of the collaborations that we've been conducting with different groups. And if any group today is listening to us, we welcome you to get in touch with us and connect with us, particularly if you're having any impact with science training or bioinformatics skills and research in the Asia Pacific region. So starting from the year 2002, we have been moving ahead. We set up our incorporation, and then we began the BWF during the bioinformatics workshop. Fiesta was a response to the pandemic. As students have been locked down, we've been various levels where you might want to study very introductory skills, you want to learn introductory skills or medium-term skills or advanced skills. All of these are available as part of the BWF, which is currently ongoing and will continue into 2022. these are available to register, and these have been hugely successful. We have trainers from all over the world joining up hands to train you in various aspects of bioinformatics. So, and we also now have an education and training portal. The INCOB has reached its, we started our social media connections just a few years ago, and we hope to make wider connections. And that brings me to this event, the International Symposium of Bioinformatics, yet again. So it began, as I told you earlier, began in Jakarta, 2017 in Indonesia, and then we went to Selangor in Malaysia, the fireflies center of the world, the most beautiful place on the planet, I would say personally for me. And then we came to Punjab in India. And we, again in 2020, we were in Andhra Pradesh in India. And this year, in its 5th avatar, INSYB has been hosted at the, at the BILSUB in Istanbul, in Turkey. So we have, as you've heard Aisha tell how hugely the registrations have impacted the kind of experience we've had with people in showing an interest before. And I really feel so many countries that have kind of unity and diversity that we have for bioinformatics. And so this particularly is a historical milestone for INSYB. And I do hope that INSYB grows and grows farther and farther with this, and wider with this. So the community milestones that we've had within the APBioNet, again, are about I spoke about the bioinformatics workshop Fiesta. The Goblet events were brought to Asia for the first time just 2 years ago. And we now have a registry of bioinformaticians, which I encourage you to join, whether you're a student or whether you're a trainer, teacher, academic, or researcher. Please feel free to join the registry of bioinformaticians. We also have a students' council in the APBioNet for students to come together and discuss things with each other and run, small workshops or events or discussions or panel discussions with students in other countries within the Asia Pacific Bioinformatics Net, within the Asia Pacific region. If you're interested in being part of the APBioNet student, we also have the bioinformatics grant challenges, which are currently underway. We are trying to put these together for the next 10 or 20 years for the world. And there's very interesting APBioNet talks and volunteer programs. If you'd like to hear more about these, please take a look at our website, the APBioNet. So we've been crashing ceilings in a lot of ways, but I'm very happy that INSYB has really come out of its shadows and done the most incredible kind of crashing ceilings this year with the huge diversity that it has managed to connect with by means of the, by means of this symposium that we are flagging off today. We've also had very interesting education tracks and community tracks in the INCOB that we finished last month. These are available on YouTube, and we welcome you to take a look at the kind of communities that we are together with. You can see on screen some of the pictures of these communities that we brought together and intend to work together with, particularly in terms of the short training format efforts that we want to do in the digital era, knowing that students have a shorter attention time span, and within that, they want to be able to pick up something interesting and enhance their skills and so on. So the entire bioinformatics education is moving in a new kind of direction. You're more than welcome to become a member of the Asia Pacific Bioinformatics Network. There are huge benefits for the community, for members of APBioNet. You would get, of course, we are all virtual, but when the world becomes a better place, and I'm hopeful that it will happen soon, regardless of the Omicron, we would have travel fellowships for our students as we used to in the olden days prior to the pandemic. We will also have, there's outreach, and there's an opportunity for you to lead APBioNet, irrespective of whether you're a student or a principal investigator. Either way, you can lead APBioNet in your own way, in your own region or globally, and you're more than welcome to therefore join us. Thank you very much. This year, once again, kudos to the organizing committee for working so hard, for being able to connect such a huge diversity, this historical milestone that you have achieved, especially Aisha and Esra. I'm very, very impressed. And I can only tell you that APBioNet is hugely grateful to you for the work that you have done together with the entire team that you have over here for the INSYB. And So before I end, on behalf of the APBioNet, I would like to thank, of course, the Beykoz Institute of Life Sciences and Biotechnology, BELSAB, of the Basmalium Vakif University for organizing this event, and also to the International Society for Computational Biologists, the ISCB, and the Regional Students Group, the RSG Turkey, and the Scientific and Technological Research Council of Turkey, it's called TUBITAK, for their strong support for this event. Please have a very enlightening symposium. I hope you'll enjoy it as much as I.
Thank you, Dr. Yadav. Thank you so much for appreciating us as well as for being here with us. Actually, we really appreciate that. And thank you for introducing in such detail APBioNet. I'm sure there will be many who will be willing to join, and we encourage everyone to join the Asia Pacific Bioinformatics Network and other organizations that are under there. Thank you so much. So now we will I will pass the mic to Ms. Nehan to take over from here.
Thank you, Dr. Yadav, and thank you, Dr. Ayşe. Our next guest is Mr. Yasin Kaya. He is representing the Regional Students Group of International Society of Computational Biologists in Turkey. So over to you.
Thank you very much, Nihan. Today we are grateful for being here and also having partnership with APBioNet for this excellent symposium. And I think today is a great day for bioinformaticians and computational biologists. We will listen to very hot topics in bioinformatics and computational biology, and also get to know inspiring researchers. So thank you very much for organizing this symposium and your amazing efforts. I have very little presentation about computational biology in Turkey and also ISCB Turkey mission. Can you see my screen?
Yes, we can see.
Okay, that's great. Thank you very much again. My name is Yasin. I'm a PhD student at Hacettepe University, and also I'm long-term volunteer and chair of ISCB Turkey. Computational biology and bioinformatics actually relatively new and fast developing area in Turkey. And recently, actually several groups are performing high quality research in Turkey, and the number of students and young investigators dramatically increases day by day. As we all know that Turkey has more than 10 universities, especially in graduate school programs related to bioinformatics. And we have actually more than 100 biotech companies that specialize in bioinformatics. Today, actually, ISCB Turkey acts as a bridge between the several universities and societies in computational biology and bioinformatics. And we are a nonprofit community consisting of early career researchers interested in these topics. And we are a formal member of International Society for Computational Biology as dependent to Student Council as a student group of Turkey. And we are one of the 28 active countries in computational biology. So this picture is the milestone of computational biology and bioinformatics activities in Turkey, driven by ISCB Turkey community. We have established in 2011, and step by step, actually, our activities in computational biology increase with numerous initiatives. We have annual student symposiums actually since 2013 and 14. In the last years, actually, ISCB Turkey has become one of the most well-known academic societies in Turkey. So we organize many hands-on workshops, panels, meetings, webinars, career fairs related to bioinformatics to attract and train the undergrad and graduate students. So to be honest, I'm personally proud to be part of this excellent community, and we are proud of our contribution to development of bioinformatics in Turkey. I actually strongly recommend you to join our community, and you can follow us on social media to be inform our events. And I would like to remind you about our panel session about current topics in bioinformatics and computational biology, actually, at the last day of symposium. So we have special guests for this panel. And actually, finally, we're proud to be part of this excellent symposium. And we welcome you as ISC Turkey and hope you all fruitful and great symposium. And thank you very much for your attention.
Thank you, Mr. Yasin, for this informative introduction to ISC Turkey. So now, ladies and gentlemen, we will be taking our break for resuming with our keynote speeches for this morning. It's a 10-minute break, actually 30 minutes break. We will resume at 10:30 a.m. in Turkey Standard Time. Welcome back after the break. We begin our keynote talks now. I would like to invite Professor Dr. Atilla Akdemir as the session chairman. Professor Dr. Atilla Akdemir is an academic member of Faculty of Pharmacy at Bezmale Vakıf University. The floor is yours.
So Nihan, thank you very much for your nice invitation. Let me bring up my slides. Just need, sorry. Okay. Okay, so thanks again. So a warm welcome and a good day to all participants. Today we have a very strong lineup with keynote speakers. The first of them will be Chris Oostenbrink, Professor Dr. Chris Oostenbrink. So Chris is from the Vrije Universiteit Amsterdam, where he did his master's thesis, actually 2 master's theses on chemistry with specialization in theoretical chemistry with Professor Eva Jan Barends, and a second thesis in the medicinal chemistry with Professor Dr. Wilfred van Gunsteren and Nico Vermeulen, the first being from ETH in Zurich. Afterwards, he's continued with his PhD, again with van Gunsteren at ETH in Zurich. And after the completion, he became part of the group of Nico Vermeulen in the Complete Molecular Modeling Laboratory, where he worked as an assistant professor. And currently he is head of the Institute of Molecular Modeling and Simulations of the University of Natural Sources and Life Sciences in Vienna, Austria. So his research interest lies in the correct description of complex biomolecular systems. And for this, you need reliable molecular dynamic simulations with accurate descriptions of molecular interactions. And for this, and this is exactly what Chris is going to talk about to us today. So Chris, the screen is yours.
Very good. Thank you very much, Attila. I think you might have to stop sharing screen.
I thought I had it.
Do you see my screen now?
Yes.
Very good. Very good. So thank you very much, Attila, for this nice introduction. And thank you very much to the organizers for asking me to present our work here. I'm very proud to, it's a big honor to kick off this session this morning. And indeed, I would like to go back to the fundamentals. Was this the subtitle of this symposium? And I'd like to show a little bit about what we've been doing on the fundamentals. So the title of my talk is Free Energies from Molecular Simulations. I will talk about force fields and molecular interactions. And really the fundamental part of molecular simulations is basically the force fields. That's the underlying way how we calculate interactions between molecules. So I would like to talk a little bit about force fields and then about aspects that are very often ignored in molecular simulations and how we address that also again in relation to the force fields. Post-translational modifications are very, very important. And then at the end, when we still have time, I'd like to go a little bit into even more elaborate ways to quantify interactions between molecular entities by doing free energy calculations. And I'll show you some examples of that. So if we say that force fields are the basics of molecular dynamic simulations, then maybe we should first have a thought about what a force field actually is. So a force field in principle gives us the molecular energy as a function of the coordinates. And we know as a chemist, we would know how to calculate that, but that comes from quantum chemistry. Bonds are made by electrons. So what we would need to describe is how electrons move around the nuclei. And then we would need to solve the Schrödinger equation. Here you see the time-dependent Schrödinger equation. But that seems to be rather difficult. You get all kinds of orbitals, and this is a very elaborate calculations. And if we're thinking about biomolecular molecules, about proteins, then typically they're still too big to be really treating them as a collection of nuclei with electrons flying around it. So what we're doing is we're trying to approximate the complex, the difficult solutions of the Schrödinger equation by defining simple energy terms. So we basically split up all the interactions that we can think of in a molecular system, and we describe all these terms by very simple energy functions. So we say, well, a bond is a harmonic term which is dependent on the optimal bond length, the bond length that we calculate from the coordinates. We take the square of that, multiply it with a force constant, and that gives us a bond energy. And we do this for all the bonds. We do something similar for all the angles. We do something for all the torsional degrees of freedom. And we calculate all the pairwise interactions between particles. Every particle interacts with all the other particles in the systems, and they do this through either a non-bonded and a non-polar interaction, which we describe with the van der Waals or the Lennard-Jones potential in this example, or they interact electrostatically with through the Coulomb interaction. And what I would like to emphasize is not so much these equations here, but that the force field basically is an empirical description of this energy as a function of coordinates. So if I know what my molecule looks like, I should be able to calculate the energy, and I should be able to calculate the forces on the atoms. And what we need for that is what the thing of the force field is. It is a collection of parameters. We need to know what force constant to use for this particular bond. We need to know which partial charges to use for this particular charge-charge interaction. So we need to parameterize a force field. We need to determine all these different parameters of the force fields to be able to approximate the energy. And this is something that has been going on already for 40, 50 years. And the force fields are constantly being updated and developed. So what I would like to show here are actually two very, very old slides that I created already, or the work was done in 2003, 2004 during my PhD at ETH. But one way that we do this in the Gromos force fields is by trying to tweak the parameters such that we can reproduce experimental thermodynamic data. So here we're looking at a picture where we see lots of different pure liquids that we simulate, and we compare what the experimental density is and what we can get out of a simulation in terms of the density. And then we tweak the parameters such that we get as close as possible to this diagonal line. Yeah? And then the details is, so here you see two different colors, you see two different force fields. We improved from the 45A3 to the 53A5 force field. For some, we had a good improvement. For others, we actually did not get so much better. We even got worse for acetone. That is then because we were making choices that we want to have also as little of those parameters as possible. So we enforce that a ketone looks similar in all kinds of molecules where we have ketones, and then the acetone actually did not work so very well, but in favor of a butanol and a pentanol, for instance. Similarly, we can look at the heat of vaporization, again, experimental values, and what we get out of the simulations that we try to be along the diagonal line. Now, as simulations became more and more elaborate over the years, this could also be done on more and more elaborate properties from that one can calculate, properties that take more time to calculate. So the next step was that we tried to look also at solvation-free energy, and that's very useful because that's basically the balance of where molecules like to be. Huh? Do they like to be in water? Do they like to be in a non-polar environment? So here we have two kinds of solvation-free energy, solvation in cyclohexane, solvation in water. And that's very important if we can capture that for the amino acid side chains, yeah? Because we need to strike the correct balance of whether an amino acid in a simulation would like to be in water or whether it likes to be in the core of a protein. That will be super important if we want to describe protein folding, and for instance, if we want to describe how proteins form stable structures. Or actually also for non-structured proteins, the intrinsically disordered proteins, it is also very important that you have the correct balance, that your amino acids actually don't stick too much together, and but form a bundle of structures. So here, this is difficult. This is more difficult to do, but we could optimize our parameters for all the amino acid side chains to reproduce the experimental solvation in water within 0.9 kilojoules per mole. Within in cyclohexane, it's about 2.2 kilojoules per mole. So this was a great improvement of the force field already. What we excluded in this picture here are actually the charged amino acid side chain. So here there is an arginine, but it's actually the neutral form of arginine, and there is a histidine, it's a neutral form of histidine, and the glutamate and the aspartate, those are in the protonated states, basically. Because for charged molecules, it turned out to be a lot more difficult. And that comes from the fact that we are simulating really very, very small systems. So what if you think of a charge in water, a charged group in water, ideally you would need to look at it in a macroscopic scale. So like 30 nanometers sized system. There's pure Coulombic interactions, and that becomes very, very difficult to do, because what we are simulating is something in a box of maybe 5, maybe 10 nanometers, but not typically 30 nanometers. Also, measuring these solvation-free energies for ions is actually not so simple. This is a very elusive property, because you need to define a reference value for the proton, basically, and that's not so straightforward as well. So it took a couple of more years before we could actually do this for the charged units as well. But then with Maria Rijf, we were able to do this, and we have again experimental hydration-free energies. You see the scale is actually way, way bigger than we had before for the neutral species, and the calculated hydration-free energies from our simulations, and we went from the triangles to the circles, so we could get more on a diagonal line. Now, this is all very nice, and we can create this way. We can create force fields that are very realistic in the description of where molecules like to go and how they interact also within a protein. But it's still a lot of tweaking and searching for parameters. So I would like to just show one slide of a current development. We already heard in one of the earlier talks or introductory talks this morning that there's a lot going on about deep learning and machine learning in the biosciences. Also, actually, in this area, there's a lot going on there. So there's efforts to try and possibly get new generation force fields, or to even avoid force fields, avoid all the parameters in the force fields, where people are trying to do deep learning as an alternative to learn energies and forces from the coordinates. And basically what we do here is we take a whole big set of coordinates for our system. And this is now a super simple example. We have an iron here in water. We take a whole bunch of coordinates, we do the quantum calculations on those systems, and then we train a neural network to learn from the 3D coordinates of the of the atoms. We try to learn what the energies and the forces will be, so that it actually can predict without having to repeat the quantum calculation. And that is a great opportunity, because first you have to do, of course, a lot of quantum calculations and you have to learn a lot, but then you have a neural network, and evaluating such a neural network is actually much faster than doing the actual quantum calculation. So what one can do is we can have a set of coordinates, we put it in a neural network that predicts us what the energy according to the quantum calculation will actually be, and then we can use that to propagate our system and to do molecular dynamic simulations. We use here an adaptive sampling scheme where where we actually calculate two neural networks, and if they don't agree with each other, then we say, well, there's something fishy. Our neural network doesn't seem to know this configuration very well yet, and then we retrain the network with additional snapshots. This is all very, very new. I just finished yesterday our manuscript on this. There's a lot going on in this field. And in this movie, what you see here is what I consider a great success, describing the interactions between transition metals and waters, or transition metals and organic molecules, is actually very difficult in force fields, because the quantum chemistry actually plays a big role. So what we see here is a simulation where there is a core region that is the iron, and the buffer region around it that's treated quantum mechanically. And around it is our force field water, or more of our force field waters. And what we see here is that after we pulled away one of the hexa-coordinated waters, it actually another one comes in spontaneously. So we have an adaptive scheme where water molecules can turn into a quantum interaction. So we can describe our molecular interactions really at the quantum level at a fraction of the costs during the simulation of the actual quantum calculations. So this is a very promising field where I expect that in the next couple of years, we will see a lot of developments going on. So far, I don't have very much to say about that yet. So I would like to actually talk more about still the force field simulations as well, and about aspects that we have been very largely, very often been ignoring in the field. And this is post-translational modifications. So post-translational modifications are very often ignored in simulations. There are very, very many of them. So the amino acids are very often modified somehow. Why do we ignore them? Well, for instance, because we don't see them in the experimentally determined structures. They were actively removed because the experimentalists, so when we solved structures, they didn't know it or they missed it even. Or very typical, we express proteins in E. coli and they don't make these kind of modifications that the human cells might do. So we have used an expression host to generate your proteins, to express your proteins and to crystallize it. And then we miss out on those post-translational modifications. Also, if they are seen in crystal structures or in NMR structures, very often as the simulation people, we don't really know what to do with them. We don't have our appropriate force fields for them. Then we remove them from the X-ray structure and say, well, let's ignore them. So we cut them away. So very often this is not very carefully done. And a couple of years ago, together with Bojan Zagrovic from the University of Vienna, we were building up a database of more than 250 types of post-translational modifications, and we parameterized them also in our GROMOS force field. So there is an online resource where you can upload your protein, you can make your modifications, and what you get out are the force field parameters that you need to describe these post-translational modifications. And there's really very many of those. So there's a whole bunch of different kinds. And people know phosphorylation, there's acetylations, methylations, hydroxylations. There's all kinds of terminal ones. So there's really a lot of different post-translational modifications. And we cover a big portion of them. So the ones that we have in the Vienna PTM is a big portion. The other, of course, that's like all the rest. That's where we cannot cover everything. So we can do quite a lot of post-translational modifications. And this was also difficult. We parameterized them initially by guessing parameters, by creating parameters by analogy to other functional groups. And then here and there we had to tweak them a little bit, but actually the agreement with experiment was quite good. So by translating what we knew from the force field of the amino acids, by translating that to the post-translational modifications for the compounds where we had experimental data, we could again recalculate and compare the hydration-free energies, the free energy of solvation against the calculated ones. And we get again pretty much along the diagonal line, and a root mean square error of 4.2 kilojoules per mole, which is quite reasonable. It's considered basically chemical accuracy. Also, we updated this then for the charged groups, for the phosphates, again, as is a similar way as I mentioned earlier. So we are now able to do many, many post-translational modifications. There's one, though, that I would like to talk a little bit more in a bit more detail about. And that is glycosylation. Glycosylation is still a very, very challenging task because it's a very important class of post-translational modifications, but they're huge. Very often we don't realize how big glycans on proteins are. So many, many organisms glycosylate proteins, and there's different kinds of glycosylations. There's N-glycosylation, O-glycosylation. So there's asparaginins that can be glycosylated, and they can have either mannose, trees, but these are all big trees of sugar. Every of these symbols is basically a six-membered sugar ring, right? So there's like a whole bunch of them, and these form big trees that cover the surface of our proteins. So we have high mannose, we have hybrid ones, we have complex ones. The O-glycans, they're typically a little bit smaller. They consist of 2 or sometimes 1 or maybe 3 or 4 sugar moieties, but they also are playing a very big role in this. And they're even more often ignored in molecular simulations because they're very flexible. So very often we don't see them in crystallization. We even cut them away before we crystallize it because otherwise the proteins don't crystallize, which makes sense. The glycans tend to play a big role in keeping proteins soluble, but then they don't crystallize. So we cut them away. And also there, if we see them in simulations, very often we just throw them away and we don't treat them. So we figured that this was something that we needed to look at in more detail. And we were doing this with Ayşegül Turupçu, who was a PhD student in my group. And so then what did we do? We looked at all these sugars. We looked at all these glycans, and initially we started to look at the individual linkages between sugars. So we have two sugars in these big trees, and they're basically like proteins. They're characterized by mainly by two dihedral angles, the phi and the psi angles as well. So around the glycosidic bond here. And then we were looking at the free energy landscape of the phi against the psi. So what are favorable conformations here in deep red? There, in this particular linkage, there are 3 favorable conformations, and there's a bunch of unfavorable conformations. We then confirmed that if we look at this in a dimer, we get pretty much the same kind of landscape as if we do it in that we look at the same linkage, but in a trimer. It's it's more noisy because the trimer, there's much more going on, but essentially it's a similar kind of shape. It's a similar kind of behavior. And then we could compare this again to observations of experiments. So we could look at where the molecule, what kind of values are observed in the crystal structures and NMR structures that are available. So you see that what we predict here to be the deepest minimum, the biggest area. Indeed, most crystal structures show structures in that area. And then we did this for all relevant linkages that we could find, for all relevant linkages in these N-glycans initially. So we did it for all possible linkages. So every one of these plots is one particular connection between a mannose and a glucose or a glucnak, or between a galactose and a mannose, and the different kinds of linkages. So we have many of those, and we established these free energy landscapes for all of them. And then we can use this to actually enhance the sampling. So I already mentioned that these glycans are very, very flexible, and they can take many, many different conformations. And now, knowing this energy landscape, we can actually put a bias on it, and we can make it easier for them to sample the different conformations. So that's what we do. We use something that's called local elevation. Many people also know it similarly as metadynamics. And what we then can do is we take a single glycan and we just simulate this glycan. So there's an asparagine here, a single asparagine, and then the complex type glycan here. We simulate it in water, we get a bundle of structures. If we use this local elevation, we get a much wider bundle, basically. You don't maybe see the difference here so well, but we're sampling many conformations. Then we cluster those, we identify the most relevant ones, and then we can put those back on a protein. So here we have now a method to actually immediately see how a protein surface might be covered. And this is also coming back to what I mentioned earlier. The glycans are actually very, very big in terms of in terms of size if you relate it to a protein. So here we have an average size protein, something like 200-300 amino acids, a relatively small protein maybe. And here's the glycan attached, or all the possible shapes of the glycan that we could find that would fit onto that protein. So we removed everything that clashes with the protein. And then you already see that this is basically, well, it adds about 50% of the size of the protein to it. Yeah? And then if you have multiple glycosylation sites, then this becomes very, very important and very relevant. Now, a very important and currently super clearly very important target where this plays a role is the SARS-CoV-2 spike protein. We all know about the SARS-CoV-2, about the virus. And basically, these spike proteins that are covering the surface of the virion are also heavily glycosylated. Viruses do that on purpose, of course, because they glycosylate. If they have the glycosylation that takes place when the virion is being created is making use of the human machinery. So it basically adds human glycans to the surface of the protein. And that means that if a virus protein covers itself with glycans, it automatically has a shield basically that looks human-like. So it's a great way to evade the immune system, because you cover yourself with something that is really human-like, and then antibodies might not recognize you so quickly as being a foreign piece. This picture is a little bit wrong. There's actually a stalk missing, but we're already very, very quickly. That's super impressive and surprising in a way of this pandemic. I think that already in March 2020, the first cryo-EM structures of the spike protein were being available, but they did not have glycans on it. They did not see the glycan structures on it. So we created models where we added these glycans on it, and you see that really a big part of the surface of the protein is being covered by these glycans for the for the spike protein. So that's a very crucial addition to the protein. And it goes actually on, because what does the spike protein do? The spike protein is responsible for the first interaction with human proteins, basically. So we have a human angiotensin converting enzyme, ACE2, that binds here. And then those two actually bind with each other, and they bind through a protein-protein interaction. But the glycans play a very big role. So the glycans both on the spike, but there's also glycans on ACE. So ACE2 is also glycosylated, and they are making a very strong, they affect very much this binding of the two as well. So on the one hand, the glycans on the spike, they actually interact with glycans and also directly with the ACE2, and the glycans on the ACE2, they seem to be actually protecting us against the virus to a certain level. So we created these models of the full systems, and we simulated this. This was now a huge system. So this is about 2 million particles if we have solvent around it as well. And then we simulated this, and we looked in particular at the behavior of these glycans. What do they do? And in particular, we focused here on the glycans actually of the ACE2. So we were looking at the glycans on the ACE2. And where they are, well, what they look like basically. Now, if we just look on the ACE2 itself without the spike being there, then you can see a certain cloud of where these glycans like to go. They're very flexible. They go all over the place. And then if we look at what this looks like when we have when we have the spike bound, then they become more focused. They actually need to move out of the way, basically, for the spike to bind, or the spike pushes them away. And that is, in a way, a bit of a penalty, basically. Yeah? So the glycans on the ACE sort of make it more difficult for the spike to actually bind, for the virus to actually bind. Now, then we were thinking that we could use that. So then people from APBioNet Biologics came to us and they asked us to look at this, because what they are developing is a product that is a soluble version of the ACE protein. And the idea is that if we give patients a soluble version of the ACE protein, that this will cover the spike, and the spike will not be able to bind to the ACE that is on the surface of the human cells. So basically, this is a perfect inhibitor because it's a perfect binding site, of course. So it will very, very strictly bind. And the idea was, if we now find that these glycans on ACE actually make the binding of spike a little bit more difficult, that if we remove those glycans on ACE, that then we could make the blue one here, the soluble ACE, bind tighter to the spike, and then there will be an advantage to cover basically the spike with the blue ones, so that it doesn't attack the gray ones. So removing the glycans on the ACE would be a good advantage. It could be of an advantage. Now, we were very lucky. We were able to test this hypothesis that came from the simulations, also experimentally. So if we just look at the binding affinity, then indeed the binding affinity, if we hear different variants where we removed one glycan, two glycans, or all of them, then the binding affinity indeed becomes tighter if we remove the glycans, but the effect was not very, very big yet. If you look, however, at the viral infections, so now we are infecting cells, then we give ACE to basically to block that infection. And this is a measure of how good that works, basically. So what you see here is the wild type, soluble ACE2 wild type. That's our base here. And then already at only 10 micrograms per milliliter, if we give the deglycosylated version of ACE, we find that we have a much, much, much more tight or stronger antiviral activity. At higher concentration, it also works for the other variants much better. So deglycosylating the ACE indeed makes it much more powerful to take off some of the to avoid infection of the spike by the virus, or the infection of the cells by the spike, by the virus. All right, I need to have a quick look at the time, because Attila, how much time do I have? I'm basically at the end of where I should end now, or?
You can have additional 5 minutes, if that's
I can still do a few minutes, all right. Yes. Then I would maybe very quickly jump to how we do these free energy calculations, because I started with saying the force fields and we do free energy calculations. And what I would maybe like to say a few words then still about how we do that. And for that, I would like to introduce you to this picture here. So this is a bit of a technical story now, but I'll try to talk you through it. So what we can do is, if we want to calculate the free energy difference between two molecules or between two states of the molecules, a solvated and an unsolvated state of our two molecules, then we need to sample these differences. And the free energy can be estimated from a simulation by looking at this equation. And this equation doesn't matter so much what it exactly looks like, but this equation works if the two molecules or the two states look similar. And what I can represent that with is how they're sampling in conformational spaces. And then you see that there's these, in this case, they would not be very similar. There's no overlap. So what I would like to have is that they have overlap with each other. Unfortunately, often they do not. And then the classical way of calculating free energy differences is by creating intermediates. So we put artificial intermediates in between there. And then for many years already, we've been looking at methods to do this with a one-step perturbation, where we say, instead of creating lots of artificial intermediates between our molecules, we are actually looking at creating a single intermediate. And we're creating a single intermediate that could look like both at the same time. Jump ahead a bit, and then the ideal way to do that would, of course, be not to create something that looks like this, that is sort of covering both my two molecules, but to have exactly overlapping two molecules with each other, to basically create a fake molecule that samples exactly the red distribution and the green distribution. So this is something that we can do with a method that we call EDS, enveloping distribution sampling, and we recently developed an improved version of that, which is an accelerated EDS. I just wanted to show basically that what we can then do is we can simulate in one go, in one simulation, we can actually generate configurations that look like the red one and like the green one. And the nice thing is that we cannot just do that for two states, but we can do that for many states simultaneously. So I'll just jump here to the final example. Sorry that the explanation is a little bit short. But what we do here is basically we create such an EDS Hamiltonian, an EDS reference state, a simulation in which we sample to one particular protein these 10 different compounds simultaneously. That means during the simulation, it sometimes looks like molecule 1, it sometimes looks like molecule 7, it sometimes looks like molecule 4, and it jumps through all the different molecules. And that's a great advantage, because that means that from a single simulation, I will be able to generate, to back calculate what the affinity is for each of these compounds. So now we're talking about not solvation free energies, but free energies of binding. And I can calculate actually the binding affinity for these 10 compounds from just a single simulation of our accelerated EDS. And what you see here is, again, a very crowded picture. But what we have here is the experimental binding affinity, our calculated binding affinity, and different estimates from the literature and from our work. And what I just want to point at is what we are doing here is this accelerated EDS. We have a deviation from an average deviation from the experiment of about 3.4 kilojoules per mole. So we have a quite decent agreement between the experimental and the calculated values, and at a much lower cost, so at much faster simulations and much more efficient way to do it. All right, I see Attila is turning on his camera, so that means I should be wrapping up. I would like to do that by still thanking a lot of people, thanking the members of my group, and thanking in particular for the story about the spike protein, our experimental colleagues all over the world. I would like to thank the funding agencies on the right-hand side here. And I would like to thank you very much for your attention, and I hope that I will be able to answer some questions.
Thank you very much, Chris. It was a great talk. There's always a lot to learn from you. So next time I'm going to double book you, because there's a lot of information there that we need. So there are some questions. So let's go very quickly through them. One is asked by Asif Khan about this ACE2 as a potential inhibitor of SARS-CoV-2 virus. So he asked whether there are some plans to commercialize glycosylated ACE2 as an inhibitor, and whether you would expect the broad spectrum of actions against the many variants.
Yeah, so that's one of the biggest advantages, of course, of this approach. So yes, of course, APBioNet is trying to commercialize this. So the company that came to us initially, they're trying to do this. The ACE2 as an inhibitor without the deglycosylation is currently in clinical trials. So this is actually being tested also on patients. There have been very successful but individual anecdotal cases where people have been treated with this. But the strongest advantage of this approach, of course, is that the variants of concern will have a hard time to avoid binding to ACE, right? Because the aim of the spike protein is that it should bind to the ACE2 protein of the humans. So it will not come up with mutations that it doesn't bind to ACE2 anymore, because it wouldn't work anymore. So the soluble ACE is basically the only way that you can ensure that there won't be variants that can evade it very easily, basically. Yeah, you never know what the virus can come up with, but there's papers also coming out where they tested this, that the ACE2 is actually binding to all the variants of concern currently.
Okay.
Very good question.
Okay, quick questions. There's some question from Aisha that she asked whether PTM, what theoretically the influence or the effect of PTM on MD simulations would be, but that's already covered by some of your slides, I think. But if you have some comments on this.
There is a lot basically that the PTMs do to the MD simulations. In particular, of course, if you think about these glycosylation, it's huge. So you can expect that the dynamics of your protein is affected, and sometimes they're very specific. We know phosphorylation can have a huge effect on the function of an enzyme. So you would expect that you see that also in their dynamics. There will also be more accidental PTMs maybe that don't necessarily do something on the protein, or the protein still works in spite of it. But there's really a lot of potential effects, and it's something we should be just looking at much more carefully. So I'm not claiming that PTMs will change the whole world, but we should at least be aware of what they do.
Okay. So maybe just a very short question. This glycosylation is very complex, and we don't understand a lot of it. And you told us clearly that crystallization makes it difficult to see the glycosylation because of these protein contacts that are inhibited. And there is this technique now, this cryo-EM, which is evolving very quickly during the recent years. And there are some possibilities maybe there to see glycosylated proteins. Do you have any views on that? Would that help us in the correct direction, or does it also have problems with this glycosylation identifications?
Absolutely. So absolutely, there's a lot going on, and we can see more and more, basically. So that's absolutely very exciting. For this particular spike example, basically, there unfortunately still all the glycans in the experimental structure were cut to their first sugar, basically. So it was just the glucnax that you could see, and all the other ones were still truncated, basically. So it's still an issue because of the flexibility. Because they are so flexible, you don't really get high resolution images of what they look like. So even with cryo-EM and new techniques. So that's unfortunate, but it will come, of course. The development in the cryo-EM is so tremendous currently that you would expect that we can see more and more, and we can relate better and better to what they do.
Okay, thank you very much, Chris, for this brilliant presentation. I'm sure there are many more questions that I haven't seen yet, but due to limitations of time, we have to skip those. Maybe they can ask it online to us via Discord or via this the Zoom, and we can share these questions with you and the answers back to the people.
Very good. Them. Very good. Okay. Thank you very much.
Okay. Thank you very much again. It was an honor to have you here. Have a nice day. Nian, can I continue? I see that Alexandre is ready. So our next keynote speaker today is Alexandre Bonvin from the Universiteit Utrecht. He is currently director of the BioFood Center for Biomolecular Research at Utrecht University in the Netherlands. So Bonvin obtained his master's degree in chemistry from Lausanne University, Switzerland. Afterwards, he did his PhD at the Utrecht Universiteit Utrecht. Then he did some two postdocs, one at Yale University and the other at ATH in Zurich. And currently he is the head of the department, the scientific director, I should say. So he is going to discuss the specific protein-protein docking program, HADOC, which stands for High Ambiguity Driven Protein-Protein Docking. So Alexander, great that you are here, and the screen is yours.
Thank you very much, Attila. Thank you all for the invitation first to speak today. And it's a pleasure to be with you all online, even if a real meeting would have been much nicer, of course. So let me start sharing. Do you see my presentation?
Yes, it's online.
Very good. Okay, well, so I'm going to speak to you today about integrative modeling of biomolecular complexes. And this is the program. I'm going to give you a general introduction on the topic and more specific on how we are tackling this challenge using HADOC, or integrative modeling software. And then I'm going to give you a few examples of what you can do with this kind of methodology. First, to model antibody-antigen complexes. Then I want to go into membrane, because these are also challenging classes of proteins to study experimentally. And I will end up, if time allows, with some small molecule docking using a new shape-based approach. So why interactions? Well, everything in life depends on interactions. And what you see here is a nice picture of the center of Utrecht, where I'm based. We have a nice canal full of terraces and full of restaurants. And you see a lot of interactions at the macromolecular level here between people. But in our cells, interactions happen as well. And a lot of those are controlled by protein-protein interactions, among others. And you've just heard from Chris in a previous talk also how the virus is using protein-protein interactions to invade your cell. So if we want to understand how life works, not only at the macromolecular level, but also at the microscopic level, we need basically to be able to describe from a structural perspective this social network of proteins. And this brings me to the structural biology of interactions, where you see here a combination of experimental and computational methods. So if we start on the right, you find the classical structural methods to study biomolecules, to get structural information about biomolecules with X-ray crystallography and NMR, and cryo-EM, of course, these days being the three main methods that allow you to get 3D information about full complexes. But next to those, there's a plethora of other methods that will provide you pieces of the puzzle. So mass spectrometry, for example, can allow you to detect interfaces, binding regions, can allow you to detect crosslinks between molecules, which is providing some kind of distance information. The same is true of threat. You also have the small angle scattering method, like X-ray scattering, but also neutron scattering, that are providing you now information about the shape of those complexes. And plenty, and even biochemical methods that are, by doing mutations, you get information about which residues are critical for the binding and not. So when you cannot solve structures of complexes of biomolecules by the classical methods, you might still learn a lot about those systems by doing all kinds of experiments. But then you have to combine this experimental information with computational methods in order to be able to build models of those macromolecular machines. And this brings us to the left of these slides, where we find the world of computations. So you have heard already a lot about molecular dynamics and force fields from Chris' talk. You can try to model complexes using such methods. You can try to model complexes by homology, simply if you can find a template in a protein database, of course, that allows you to build a complex. And today, I'm going to concentrate mainly on using docking methods to model those complexes. But of course, we should not forget the advent of machine learning and the fantastic work of DeepMind, Google, on predicting structure of complexes. And just 2 months ago, they released a preprint where now they have been retraining their model to do prediction of complexes using AlphaFold. So there's an AlphaFold multimer version now, which allows you to model complexes between proteins. So this is also very exciting times for the entire community. But for today, we will just remain in the field of molecular docking. So what is the problem? What you see here are two molecules. So we need, when we want to model complexes, you need to have usually the starting point, meaning the structure of the component of your complexes. It's very difficult to fold and dock at the same time. And then what we have to find is do a search in the interaction space, which means you can fix a molecule in space, and then you will have to rotate the other molecule or sample all possible rotation of the other molecule and sample all possible translations of this molecule around this one and measure how good is the fit between those. And the first docking methods were developed in the early 70s by Joël Janin, Shoshana Wodak, and these were mainly geometrical fit between the surfaces of the proteins. But of course, you can use force fields as well that have been described in a previous talk to calculate the interaction energy between those molecules, and you find here an electrostatic potential and here Lennard-Jones potential. And what you should also realize, a lot of docking approach are dealing with two molecules. It depends a bit on the methodology that you're using, but many complexes or assemblies that are taking place in our cells consist of more than two molecules. So you need to be able to bring this docking problem to the modeling of multimers, basically. Now, this is a problem that we have been tackling since pretty much 20 years now, and since 20 years we have been developing Haddock as an integrative modeling platform to harvest as much information as possible on the system that you are modeling, and using classical molecular mechanics tools like energy minimization, molecular dynamics, to try to generate model of those assemblies. It all started from NMR experiments, because my lab is based in an NMR center, where you can basically map the interactions between molecules by NMR experiments, but you can also use mutagenesis, biochemical experiments, cross-linking. I mentioned it in the context of mass spectrometry, HT exchange, the same, but also bioinformatics, very important. So you can try to predict the binding regions. And one of the keynote speaker later today is going to speak of trying to predict interaction from sequence. I mentioned the shape information, also cryo-EM and cryo-electron tomography. They might not always reach the resolution sufficient to build structures from scratch, so you might have to resolve to docking-like methods to put the molecule into those shapes. Now, we have basically defined a way of incorporating a large variety of information, which is not always very well defined. So it might be fuzzy information, you might information about residues that are important for the binding, but you don't know with what they interact. But we have defined a way in Haddock to add an energy function to the classical force field that we are using that represent those experimental data. And then we are trying to optimize the system against this energy function. Now, the current version of Haddock can handle up to 20 different molecules. Of course, it only makes sense to model that many molecules if you have enough experimental data. Otherwise, the search problem is very complex and it might be a waste of computational resources. If you are looking at symmetrical assemblies, you can also use symmetry as a restraint for the modeling process. And one of the features of Haddock is that we also introduce flexibility in our modeling process to optimize the interfaces between the molecule. And over the years, we have always been putting our method to the test in what is a blind experiment for predicting the structure of biomolecular complex, which is called CAPRI. So how do we search this interaction space in Haddock? So we use a classical force field, and you've all seen the mathematical functions behind those very simple representations. So we describe the bonds the bonded interactions in our molecules, but importantly for interactions, the non-bonded interactions, so van der Waals electrostatics. And we add to that an experimental energy term that will represent the data that we have at hand. And the search itself is performed by using a combination of energy minimization and molecular dynamic simulations. The docking, the modeling itself consists of 3 stages. So in the first stage, we're going to treat the molecule as rock solid. So there is no flexibility there, but we're only sampling the interaction between the molecule. That's the initial stage. Then we're going to refine, optimize the interface of those complexes through a simulated annealing protocol where we raise the temperature and slowly cool down the system using molecular dynamic simulation. And at the end, we might solvate the system in a layer of water and perform a very, very short molecular dynamic optimization. So this is how the initial stage looks like for the 2-component complex. The spheres that you see are actually residues that were identified from NMR in this particular case as being important for the interaction. So you don't know what the pairing is, what the contact is that they make, but the restraints that we put on the system basically brings the interface together without predefining in which orientation those should be. After having done this initial sampling, and in initial sampling, we might sample between 10 to 100,000 conformations. Basically, we select a fraction of those, a few hundred typically, and then we introduce flexibility in the system. And the flexibility is introduced by default now automatically only in the interface region. And this is what you are seeing here. You see first the side chains become flexible, we optimize the interface, and in the second phase, we add also flexibility to the backbone. And you see this loop here just flipping over. So this is a small binding-induced conformational change taking place here. You cannot do miracle with the current methodologies with Haddock, but also the other software, the docking software. We are limited in the amount of conformational changes that we can describe. So one solution to that is to use an ensemble of starting conformations to the docking, and you basically dock against all those conformations. You can also try to introduce more flexibility into the system by increasing the length of this second stage in Haddock. This is something we do for the docking of peptides, which are intrinsically highly flexible. Now, if we refine the system in a solvent layer, this is what's happening now. These are very short simulations, so it's nothing compared to the real MD work. So this is not changing much the structure, but this is improving a bit the energetics. But actually, in the latest version of Haddock, we don't even do that. We only do a minimization at the end, again, for computational speed purposes. So these are the 3 stages in the current version of Haddock, and at each stage, we do a selection of models. So we have what is called in the field a scoring function. So when we do the simulations, we include the classical force field that was introduced in the previous talk, but when we score the models, we only consider the intermolecular component of that energies. And the final term of that scoring function is this one. So we have 2 terms that are let's say the classical energetics for electrostatic interactions and van der Waals interactions. So this is describing the amount of energy between the molecule. We have a dissolution energy term. So this is an empirical term, which is basically accounting for the price or bonus of removing water from the interface of the molecule. So if you remove water from hydrophobic surfaces, typically it's a good thing. If you remove water from charged residues, you have to pay a price. And this is what this dissolution energy is describing. And on top of that, we will have a term that describes basically the experimental information that we put in a system. And you see a very simple, so this is kind of, it's a linear model with 20% electrostatic, full van der Waals, dissolution, and only 10% of the experimental information. So this was optimized almost 20 years ago on a few, rather small set of complexes, and it has survived a long, many years of further optimization. You can optimize using machine learning models, and you will get, instead of 1.0, you will get 0.973711. But at the end, it's not much better. We are still limited in the scoring. Our scoring functions are far from perfect. So I like to keep things simple. But again, this has survived many years, and it's still, from a physical-chemical perspective, this scoring function makes quite some sense. And just to show you that actually it does make some sense, I'm moving now to an intermezzo, going back to SARS-CoV-2, and we've heard about that in a previous talk. So this is the work of Joao, who is a former PhD student of mine. And this is the work he did with Michael Levitt in Stanford. And so we're not involved in this work, but what they did is basically to use haddock to look at the interactions between the spike protein and ACE2 receptor. And what they were interested is to compare ACE2 receptors of different species. And you see here a lot of species, the color coding. So this work was done a year ago. So the color coding here indicates the species that can be infected by the virus. And the red ones are species that are known not to get infected by the virus at the time. And the black one, there was no information at the time. Now, if you only consider the sequence similarity between the human receptor and those species, this is not really explaining this cross-species transmission. You find a system where there's a high sequence similarity and no transmission, and you find a system where there's a similar sequence similarity and there is transmission. However, if you use haddock and its simple energetics to study this interaction, so they are not doing docking, but they're doing refinement in haddock. So they take the complex that has been modeled for all those species and just refine the system to get the scores. So the haddock scores that I just showed you, you see now that there seems to be a much better distinction between the species that cannot be infected and the one can be infected. So that's quite nice. And actually, SG Carta, which is in ISME, has been doing rather similar work as well, using haddock scoring function for that purpose. So simple energetic function force fields that we are using are still good enough to explain some of the biology of those systems. So now back to haddock. Most of our users are actually using haddock through a web portal, which we operate in Utrecht. And you see here the interface, and this is the URL if you want to go. So we have a large community of users. We have been serving a large number of docking runs. The portal has been running since 2008. And we are able to do that because we have access to a lot of computational resources distributed across Europe, but also in Asia and the US through EGI and the European Open Science Cloud. And 60% of all the computing that we have done for our users has been running basically outside our laboratory. This is just a picture of our user base with a lot of users distributed all over the world. The winner is India, and then Europe aggregated and the States. But if you look at Turkey, because we have a lot of Turkish people in the audience today, we see that we have also quite an active community of users in Turkey. Coming back again to COVID, so these are some statistics that are showing you. So this is the last 2 years, basically. We start in 2019. And this is the number of jobs that we are processing per month on a server, which was in the order of 3,000. And then the lockdown started, COVID appeared, the lockdown started, and we've seen almost a tripling of usage of our server as a result of COVID, basically. And you kind of see the waves, the COVID waves coming in. And since then, the usage has more than doubled. We started asking users, is your simulation related to COVID-19? So we have these statistics as well, and you see about 1/3 of all the simulations that we are running on the servers are related to COVID. So not only have we been doing much more work on the server over the last year, but also the number of users that are using our tool has more than doubled. And this is a sustained growth that you can see here. So we had actually to take actions to improve the machinery on the back end of the server to be able to cope with this increased demand. Also, those systems, a lot of people are looking at spike proteins with antibodies. These are large systems that are demanding in terms of computing time. And again, having a proper infrastructure at hand to do this is very important. Next to haddock, which is our flagship software, we also are operating a number of other portals in Utrecht, many of those have to do with biomolecular interactions. Like Prodigy is it's a simple machine learning model based on contact to predict the binding affinity of a complex. Bioinformatic predictors for interactions, hotspot predictors to detect or predict which are the critical residue at the interface. Some antibody-related tools and also tools to manipulate files. So all available through wmr.science.uu.nl. So let's move now to a first example of what you can do with this kind of methodology, the kind of information that you can actually use. And we move into the world of antibody antigens. So as you probably all know, the antibody structure consists of, so we have two chains with a light and heavy chain. And the action in terms of binding occurs in these hypervariable loops. So there's 3 loops in the heavy chains, and we have 3 loops in the light chain. So we have 6 binding loops, and this is knowledge. Okay, so we know that an antibody will bind to its target through those loops. So this is information in principle that we can use in the modeling, even if we have no experimental information. So we wanted to basically develop a protocol and test how well we are doing using this kind of information. And we, so this worked Francesco Ambrosetti, a former PhD student in the group. And Francesco tested 4 different software that are allowing you to use, to some extent, experimental information to bias the modeling process. So ClusPro and ZDoc are 2 famous docking software in the field that are also doing very well. And they can use the information basically to filter out docking solution, not to bias the search, but they use the information in the scoring stage, basically. LightDoc is another software developed by Brian Jimenez and Jorge, who Brian joined my team also, and it allows you to use the information basically to also bias the search. And Haddock, of course, we can use the information both in the search and the scoring. So what did we do? We tested 3 different scenarios. So on the antibody, we used the knowledge of these hypervariable loops to drive the modeling process. So we defined in Haddock that those regions, those 6 loops must be involved in binding, basically. And then we have 3 scenarios. One scenario is taking the true interface from the crystal structure as a reference, where you basically have the perfect interface. You don't know the contact, but just the perfect surface for the binding. So that's the best case scenario. It's just to define, the baseline of what is the best results achievable in this case. Then we have a scenario where you will know the epitope on the antigen to some extent. It's not perfect. So we selected all residues in a 9 angstrom region, making contact within 9 angstrom with the antibody. And in the third scenario, we assume that we have no knowledge at all of the binding site on the antigen. So the only information that we put in is that of the hypervariable loops. We tested all software using this approach, and these are the results already. So here you see a lot of different plots with colors. So what are we looking at? First of all, the columns indicates the 4 software that we looked at. So ClusPro, Haddock, LightDoc, and ZDoc. The rows correspond to the 3 scenarios that I show you. So the top row, we have no information on the epitope on the antigen. So we target the entire surface. In the second row, we have some loose information on the epitope. And in the third row, we have perfect information. Now, what does each plot contain? You see a number of, so the x-axis tells you, okay, what is actually the performance that I achieve if I only look at the first model, which is ranked by the software. Or if I looked at the first 5 model, or first 10, first 20, 50, and 100. So the more models you see for all software, the more successful you are. But it doesn't mean that you are able to score them properly. If our scoring function were perfect, we should get in the top 100% success rate. Now, the y-axis is the success rate, and the color coding tells you the quality of the model that we are generating. So if you see dark green, it means that we are within 1 angstrom of the crystal structure. So we did a very good job in modeling. Green will be an acceptable model, medium or medium quality model. So typically 2 angstrom RMSD-ID interface, and blue is an acceptable model. Now, what you can directly see is that the more information you have on the system, and this is true for all software, the better the docking results become. But it can also be seen clearly that since Haddock is really using the information in our energy function to bias the search, that you see that Haddock is doing the best consistently of all software. And we see that we are able to generate a high quality model when we have very good information. And this distinguishes it from other software. When you have no information on the epitope site, you see that things are much more, for all methods, our success rate is pretty low. If you look at top 10 model, we reach about 30%, but that's about it. So there is still a lot of improvement that can be done in this field. Now, if you want to read all the details, you can look up this paper, which was published last year in Structure. So using information really to drive the modeling process does improve both the performance in terms of number of correct molecular success rate, but also the quality of the model that you are generating. So let's move now to membrane proteins. Now, membrane proteins represent about 20% of our proteome and about 50% of all drug targets. And they are notoriously difficult to study by experimental methods. You see here a plot, so it's not up to date until the latest 2021, but you see that this is the growth of the PDB in terms of all proteins, and in orange you see the number of membrane proteins. So there have been progress in the last year in terms of number of membrane proteins that are being solved, and cryo-EM is also contributing to that, but there's still a large gap there. So we wanted to see first, how well are we doing on the system, and when you are developing methodology, you need first to define a benchmark. So we need to have systems for which we know the answer. So we have the crystal structure, ideally, of the complex, and we have structures of the component of the complex. And this is the first thing that we did, was to put together such a benchmark and then also test the performance of haddock on those. And this was published, this is the work of Panos Koukos, was published in 2018. So at this time, it was just using haddock in its default way to model complexes. But the membrane itself is providing information because your protein is sitting in a membrane. So the topological information of the membrane is something that in principle we could take into account in the modeling process. So we wanted to see if we could actually explicitly account for the presence of the membrane during the modeling process. For that, Jorge, former PhD student, and Brian, former postdoc in my lab, have been combining two docking software that we encountered already when talking about antibodies, LightDock and haddock. Now, LightDock is basically a docking software which uses artificial intelligence and the glowworm swarm optimization algorithm, where you start from basically a swarm of different orientations, and then you optimize the swarm, and the swarm, it's like birds flocking, they're going to convert to some solution. And you repeat this optimization from many different starting positions around your target protein. LightDock also has the advantage that it can incorporate information in the modeling process. So it has also been evolving as an integrative modeling platform over the years. So for doing this membrane modeling, so we are looking now at not membrane-membrane association, but we are looking at a soluble protein binding to a membrane receptor. So what we do is we take, so there is a database, memprop MD, where coarse-grained molecular dynamic simulations of membrane proteins are performed. And from the database, you can extract conformation of your protein embedded in an equilibrated membrane. So this is our starting point. So for the receptor, we extract this information. We only keep the phosphate atom of the membrane. So we don't want to have to model the entire membrane, but in this approach, we only keep the phosphate. We transform those into artificial beads. And then in LightDock, we're going to restrain the starting point of the modeling to the region which is solvent accessible around the receptor binding site. Usually you know on which side of the membrane your proteins are binding. And we also introduce a penalty during the docking if the soluble protein penetrates, overlaps with those artificial beads here. Now, LightDock is generating models usually that have clashes at the interface, so you need to refine those models. And this is happening in haddock, where we use basically the final stage of haddock to refine the complexes and declash the complexes. Now, this was tested on a set of about 18 different complexes that consist of different secondary structures. They are alpha helical protein, they are more beta sheet proteins, and they are also antibody in this data set. And you see here, again, the same plot that I show you for the antibody antigen. So again, the number of models that you consider in your scoring and the success rate on the y-axis, and the color coding, again, is the same, with dark green being high quality. So this is the overall performance for these membrane cases, if you look at all of them together. What you see in gray is the performance that you achieve if you don't use this topological information of the membrane. So you don't include this description of the membrane during the modeling process, and you see that we are doing pretty poorly for membrane proteins. There are many reasons for that, also often because the membrane size of the protein is sticky, and interfaces like to be usually interface in protein-protein interactions are often hydrophobic. So you might get a lot of false positive binding with your soluble protein binding in the membrane region of your receptor, which if the membrane was explicitly present could not be possible. Now, as soon as you have this simple bead-based description of the membrane, you can see that now the performance increased greatly, and we get about 60% success rate for the top 10 model and around 90% for top 100. Again, like in all cases, like for the antibody antigen, we still have a scoring issue, so we are not always able to tell which one is the best model out of all the models that we have been generating. So this was published last year in Nature Communication, so you can look it up if you want to see all the details. So it combines two integrative modeling software, LightDoc for the sampling and HADOC for the refinements. It does account for the membrane via beads, and actually we are also able to use HADOC in this case for efficient removal of clashes. So HADOC can be used also as a refinement tool to refine complexes, and this is being used also, among others, by some cryo-EM groups when they don't have high-resolution data, but they are modeling complexes into the densities. I should also mention that actually HADOC is able to accept membrane directly. So we had users who modeled a membrane protein and embedded in a nanodisk. So nanodisk are those pieces of membrane that are stabilized by an alpha helical protein wrapping around those. And this is basically solubilizing the system, and then you can do NMR studies. And to our surprise, actually, the server was perfectly happy to accept those systems. So in the future, hopefully, we will also have, we also been working on directly incorporating the membrane information into HADOC also for the sampling phase. Now, for the last part, I'm going to move into the small molecule world. And we have been doing small molecule modeling with HADOC pretty much since the early days. And one reason for that was that we wanted to have support for cofactors. Think of ATP, ADP, heme groups. So this might be important for the structure of those proteins. And this might also basically contribute to the binding between proteins. So from the initial developments of HADOC, we built in the support for small molecule. And then later on, we started, since the machinery was there, we were able also to study small molecule, to do small molecule docking with HADOC. I would not advertise HADOC as a way of doing virtual screening for millions of molecules, because it's computationally much more demanding than the excellent small molecule software that are there. But again, if you have information, you can put that information into the modeling directly and bias the sampling. And this is something that has been very useful also for drug design in the industry setting. Now, we have been testing our ability to model small molecule over the years by participating by the Drug Design Grand Challenge, D3R. We entered the first time in the second version of the Grand Challenge, and at that time we didn't do very well. We learned a lot, and we realized that it's very important in small molecule modeling. If you have choice between multiple templates, multiple structure of your receptor, to select the receptor smartly, basically taking the structure which contains a ligand as similar as possible to the target ligand that you want to dock. So this is what we call a templates-based docking protocol. So we select first the protein template based on ligand similarity, and we use the Tanimoto coefficients for that. Then in that stage, we were using OpenEye software to generate a lot of conformations of the ligand, so sample all possible rotatable ones of the ligand, and then we select conformations of the ligand by basically calculating the shape similarity of those conformations with the target, the template ligand that you found in this first step. So you see here the superposition of two ligands into those shapes. And then we simply superimpose the ligands into the template receptor that we have, and we don't do docking in HADOC, but we only do our final refinement. And this was a very successful strategy in round 3 and 4 of D3R. And you see here 20 models, where in yellow you see the crystal structure, and in green you see your predictions. So this is working very fine. There are cases like you see one here, maybe it's very small, but since we're only doing refinement, it's not very efficient. So if you need conformational changes, if for some reasons the ligand that you selected, of course, the ligand might be outside, might be much larger than your template ligand. So it's hard to induce conformational changes in a ligand once you have put the ligand into the template. And you see an example here. But we have this shape information. And this brought us basically to develop a new docking protocol where we are now basically using shape. So we have a template which we identified with a ligand. So this is not the ligand that we have to dock, but this is a ligand which is the most similar ligand to our target. So we transform this ligand into beads atoms. So these are artificial atoms that have no interactions in terms of energetics with the remaining of the system, but they are inside the receptor. They kind of define your binding pocket, if you wish. And then we're going to do the full docking process with ad hoc by defining restraints, ambiguous restraints between the ligands that you have to dock now and those bead atoms. Those restraints are ambiguous, meaning that for each carbon of the ligand, you would define a restraint which should position it somewhere in this shape. So basically the atoms, the heavy atoms of the ligand must overlap with the shape, but it's not defined where, with which specific shape atom they should overlap. And how you define the restraints depends also on the size. So if your shape is larger than the ligand that you are docking, then you want to define the restraints from the ligand to the shape. If the shape is smaller than the ligand that you are docking, then you're going to do the other way around, where you define restraints from the shape to the ligand. We can also encode pharmacophore model into the shape by assigning properties to the bead atoms. So like, this should be positively charged or negatively charged or hydrophobic regions. So it's then a simple, slightly more complex model, but this is also working nicely. And then we do the full docking process in ad hoc. One advantage here is by doing this, we can sample much more conformational changes. So the selection of ligand conformation upfront for the docking is much less important because the restraints are able to induce conformational changes. And then we end up with those models. So this is a very competitive protocol. And if you want to read all the details, you can see it here. So we published that quite recently, but actually we used this protocol to do some drug repurposing early last year. And we started this work in March, where we selected different targets. So the main protease, but also the RNA-dependent RNA polymerase, and also ACE2. And using this shape-based protocol, we screened about 2,000 approved drugs at the time. And you see here the top 10. So now you are doing virtual screening effectively using ad hoc. And you see here the score based, the best score obtained by ad hoc for those. So this is our top 10. A number of those ligands were actually purchased and tested in an inhibition assay for the main protease. And you see that the second one in the list and the fifth one in our list out of 2,000 were actually showing activity in the micromolar range. The problem is that those are cytotoxic to cell. So this was a basically inhibition assay of the protease, but once you give those compounds to cell, the cells are dying. We've also been doing this work in the context of a larger IMI care project. So it's an international consortium, and also a lot of companies, pharma companies, have been doing this drug repurposing. And what came out of all this work that there were no suitable approved drugs that were basically working effectively against the virus. So now in this care project, there are also new drugs, and some recent drugs have been released as antiviral. So this brings me to the end of my talk. So I hope to have give you an overview of what you can do with this kind of integrative modeling methodology. I've shown you that we still have limitations in what we can do. Our energy function or scoring function are not perfect. And what we are generating some models are not experimental structures, but models are very important because they allow you to generate new hypotheses. And with those hypotheses, you can go back to the lab and test those. And so in that context, modeling and experiments are very much complementary. And you have to see that not as a linear path, but rather as a circular path. So where are we going in this field of integrative modeling? What you see here is an artistic illustration of integrative modeling, which we created to celebrate 50 years of the protein database, which happened this year. So you see here this integration of different techniques, MS, cryo-EM, you see NMR here, high throughput assays, biochemical assays, some piece of code here, so software. So you integrate all of that to study biomolecular machines. And this particular complex is the 50 years of PDB complex. But what you see here is that it's not a unique conformation, but you see a movie. So basically, this is a dynamic landscape. So it's a dynamic complex. The complex is going to change its states depending on many factors. Where are you in a life, in a cell cycle, post-translational modification mentioned by the previous speaker. So we need to be able to characterize molecule not only in one state, but in multiple states. And so it will be important. So in terms of, say, structural biology or integrative structural biology, we will have to move to integrative structural biology of dynamical landscape. Also, the energy landscape, which is under this kind of movie that you see here, might change as function of the state of the system. So we need to add this dynamical component, and that's probably one of the challenges for the field for the coming years. I want to thank the people who have been doing the work. You've seen the picture showing up during my presentation. So this was, of course, as everyone, online group meetings over the last year. Many projects have been supporting the work and all the software development that we are doing. And currently, we are supported by EGIS and the BioXcel Center of Excellence to further develop and operate ad hoc and all the web services associated with that. And thank you very much for your attention.
Thank you very much, Alexandre, for this great talk. Also, thank you for developing these protein-protein docking tools. And more importantly, also for allowing us to use it for free, because in some research groups, the budget is a very important problem. So your software is an enormous help for us. Thanks for that. There are some questions that have been listed. I'm trying to find them. Sandeep Kumar has a question. He's asking by which we can identify, is there any way by which we can identify specific epitope interactions with 1, 2, or 3 out of 6 hypervariable regions in the antibody?
Okay, in the antibody. So, of course, once you have a model, well, all 3 loops usually contribute to the binding with the H3 loop. So the heavy side loop 3 being the most important one. It's also because it's usually the longest one. And that's the most challenging one to model because of its flexibility and the length. But once you have model, of course, you can identify what are the critical residues. So you can like decompose the energetic of your interface at the residue level. And you can try to predict, which of those residues are the critical one. And then try to test those with experiments. You can also try to, once you know decompose the energetics, this is coming back to this ACE2 spike protein work that I mentioned for cross-species transmission. So where basically they are comparing scores of different mutants of those proteins and identifying and predicting binding affinities. And that's, of course, binding affinity prediction is a long way to go. But once you have a model, again, you know which residues are critical, so you can analyze those interactions.
Okay, thank you very much. There's this other question from Lai Tai Leon about docking 3 for proteins A, B, and C, and whether you have to include the active residues of all 3 proteins. What if the active residues of B and C are not known? I think I summarized the question correctly like that.
Yeah, so again, when you move to so software like ClusPro and ZDock, for example, are excellent software to do ab initio docking, but they can only handle 2 molecules. So if you have only information on one of the 3 molecules, it's going to be a very difficult problem. So I would not trust that you're going to get very good results out of there. You might be lucky, but it's going to be very hard. if you know that there is symmetry in play, then it's a different game. But if you have only information on one of the three components of your complex, but of course, if you have no experimental data, you might still have other type of information. So bioinformatics, so you might look at sequence conservation on the surface to try to predict interfaces. And these days, you can also consider using coevolution, trying to predict contacting residues. So rather than doing a purely ab initio modeling, with information on one protein, I will try to use some of the bioinformatic tools that are out there to try to at least to predict binding sites on the other components, because this is going to help you. It's not going to be perfect, of course, but it's better probably than going purely ab initio with no information. You've seen also for the antibody antigen, when there is no information on the antigen side, the success rate was maybe 30% in the top 10 models. So it's not great. So if you go to 3 molecules, that's going to be even worse than that, most likely.
And after the presentation of Chris, a question popped up in my mind. He warned us about this glycosylation of the proteins and that we are not taking it into account to an important level, basically. So does your program or do your procedures take that into account, or is there a way to take glycosylation into account?
So this is, so we've been docking, well, there are two things. There's first glycosylation, and then there's docking glycans. So we actually added support for a glycosylated protein to the server at the beginning of the pandemic, because people wanted to model some of those complexes with glycans. So we accept now, so at this time, we only support N glycosylation. So it means the glycans that are attached to asparagine residues, because there is also O glycosylation. But we don't have that support in the server. But the server, so if you give it a glycosylated protein, and it's one of the glycans that we are supporting. So on the server page, there's information about which glycans are supported, and also which post-translational modifications. So we also support that, phosphorylation, acetylation, some of those things are there. We don't have all the modifications that are in the server that Chris described, but we have quite a number of those. So yes, we can describe glycosylations. And we are also working, we didn't publish anything, but we are working also on protein glycan modeling. So this is something that the server also supports in principle, but we have been doing a lot of work recently to properly define the protocols and benchmark the performance. And actually, there's a preprint out there where we use haddock to model the interaction of the N-terminal domain of the spike protein, which does recognize specifically some sialic acid on our cells. So they're also based on NMR data, we have evidence, and then we did the modeling of that.
Okay, thank you. Just a few more questions. The time's running up, but Lai has other questions. Whether they are able to get the entropy value from haddock, and the second one from also Lai is whether you should consider it as a flexible or semi-flexible docking.
Okay, so entropy, for a very good reason, the scores that we're reporting in haddock on the web server, for example, have no unit. So we say arbitrary unit because we don't want people to interpret the scores in terms of binding affinity. In some cases, there is maybe a relationship with binding affinity, but in general, there is not. And we have published papers about that. So you cannot compare the score of two different complexes, which means, entropy is one level further. It's even more challenging. So no, you cannot get entropy out of your modeling. You might say, if you could measure the entropy from the conformational differences of your models, maybe, but I'm not aware of any work where docking has been used to extract entropy. And then semi-flexible or flexible, well, what is flexible, what is semi-flexible? So we have flexibility in the system. We can define molecules that are fully flexible, like peptides. So in terms of, so what we are not doing is folding a protein while docking. So, fold and dock, this is possible sometimes in Rosetta. There are some protocols, but you should not expect the protein to fold. There are examples of protein that only fold upon binding to their partners. This is not something that we can describe by the kind of methods that we have. So So it's not a fold and dock, but it can be considered as flexible / or semi-flexible. It all depends on the amount of flexibility that you give to the system. But we have full sidechain and backbone flexibility at the interfaces.
Maybe we can take the final question. Asif has reshared the question of Harpreet Singh, where he says that Hadoop uses the Hadoop score instead of binding affinity. How can we accurately differentiate between various token conformations using Hadoop score rather than binding affinity?
Well, you know, there is no docking software that gives you binding affinity. Okay, they are all based on some kind of energy function, which are it's like the force field function that Chris described. This is not binding affinity. At best, it will be an enthalpic value, maybe. And this is why we say we give the score, again, arbitrary units. When you are comparing different conformations of the same system, you can compare those scores. And it's fine for scoring purposes. And it's not like you don't need to predict binding affinity for that. If you want to do virtual screening, or if you want to do to compare different antibodies binding to one antigen, then it becomes much more tricky because it becomes a binding affinity. And to get good binding affinity values, you will first need to have high trust in the model of the complex that you have. So, and we have shown that, you know, even taking crystal structures of complexes, there are no scoring function or docking software out there that is able to give you good correlations to binding affinities. And that's one reason why we developed a model Prodigy, which is based on contacts to predict binding affinity. But so you don't need binding affinity to decide what is a good model or not within one set of docking for one complex.
Okay. Thank you very much, Alexandre, for this great talk and for the clear answers to the questions. There are many more questions, but it would be difficult to ask them you this because we have a little bit shortage of time. I will collect the questions and send them by email or other ways to you, and we can share the answers with the participants. So thank you again for this great talk, and Jan, the floor is yours.
Thank you very
so
much
again. Professor Attila. Thank you so much. And our keynote speakers, Dr. Chris and Dr. Bonvin, for your enlightening talks. Thank you so much to you. Time for a lunch break. Then we will come back for our first poster and oral presentation sessions. We will use the same Zoom link. Then you will be able to choose your breakout rooms for the parallel sessions. We will begin at 1 p.m. Turkish Standard Time. Thank you and enjoy your break. Good afternoon, everyone. We will begin in 10 minutes. Thank you. Welcome back and thank you for joining us once again. We began our first oral and poster presentations. We will have two parallel sessions, one for CADD SARS-CoV-2 and the other one for big data analysis, biotools, and general bioinformatics. Please join your desired breakout rooms from breakout room tab in lower right on your Zoom.
Hey Anton, hoe is het?
Mute. Ja, zo beter. Kun je me horen?
Gaat alles goed?
Ja, goed. Ja, bij jou ook?
Ja, heerlijk. Hoe is het weer daar zo?
Ja, fris, maar wel af en toe zonnig. Niet te veel regen. Redelijk droog eigenlijk wel, dus dat is best goed voor een Nederlandse winter. En bij jullie is het nog warm? Of,
Nou, het is niet echt warm, maar zo rond de 15, 20 graden.
Nou
maar,
ja, dat
na het weekend wordt het wat kouder, geloof ik. En ze verwachten sneeuw met oud en nieuw.
Oh ja, oké. Nou, sneeuw hebben wij nog niet.
Hoe is het in de groep van heer Jaap Heringa? Je hebt het heel erg naar je zin?
Ja, heel erg. Ja, ik zit er ook al heel lang natuurlijk. En ja, dat is een fijne groep. Er is natuurlijk heel veel gebeurd de afgelopen paar jaar. We zijn verhuisd naar een nieuw gebouw en de afdeling die groeit enorm. Dus dat is wel, dat is wel spannend op bepaalde momenten. Maar ook wel weer leuk, want dan gebeuren er weer eens nieuwe dingen. En veel thuis zitten de afgelopen jaar ook. Dat was ook wel een uitdaging op verschillende manieren. Maar ja, gaat goed. Ja.
Ben je dichterbij verhuisd naar de vuur toe? Je woont op een grote afstand, hè?
Nee, ik woon nog steeds in hetzelfde dorp.
Okay.
Een uurtje rijden nog steeds, ja.
Oké, cool.
Ja. Nee, we hebben hier een heel prachtig plekje, lekker rustig en mooie natuur en veel rust in de omgeving. Dus,
dan wil je daar natuurlijk niet meer weg.
Nee.
Nee. Ik woon dicht in de buurt van een universiteit waar ik werk. Alleen het is heel erg druk. De Unisstad natuurlijk, Istanbul. Er is bijna geen verschil in dag en nacht. Het is constant druk. En ik mis wel de rust van Nederland. Het is heel anders natuurlijk. Toen we in Nederland waren had je het nog niet echt door. De rust was vanzelfsprekend. Maar hier, de drukte van een grote stad.
Ja, Istanbul is iets groter dan Amsterdam, hè?
Ja, ze zitten zo, het is ongeveer 15 miljoen, 16 miljoen.
Ja, dus dat...
15, 16 maal.
Ja, dat is... Ja, dat is bijna net zoveel als in Nederland.
Oké. Doe je nog aan molecular modeling en docking studies, of ben je daar vanaf gestapt en ben je meer richting bioinformatica gegaan?
Sorry, het eerste verstond ik niet goed.
Doe je nog steeds moleculaire dynamica simulaties en docking studies?
Ja. Niet zoveel als bij scheikunde. Maar ik zoek ook wel de grenzen op, zeg maar, de combinatie van de biofysica en de bioinformatica. In mijn recente papers niet, maar als je 5 jaar terug gaat of zoiets, heb ik nog wel nog iets gedaan met uitrekenen van de potential of mean force tussen 2 eiwitten. En dat is natuurlijk gerelateerd aan dit werk, maar dan vanaf de biofysica kant.
Oké.
Ja.
Right. Dus we nu ongeveer beginnen, geloof ik.
Ja.
Ik zie Nian daar.
Hallo.
Hi. Welcome back, everyone. I hope you had a good scientific sessions. Our last speaker of the day is Dr. Anton Feenstra. I would like to invite Professor Dr. Attila to be chairman of the session. Over to you, Professor Attila.
Thank you, Nihan. Anton, it's an honor to introduce you. Anton has obtained his PhD from the Rijksuniversiteit Groningen in the group of Berendsen. So that's the person that is responsible of development of the GROMACS software package, and Anton has been part of the developing team of GROMACS. Then he went to VU University of Vrije Universiteit Amsterdam, and he worked at the molecular modeling group of Nico Vermeulen, the molecular toxicology group over there. And afterwards, he went to the bioinformatics department, still at the VU University Amsterdam, where he is still employed. And today he will discuss his work on the prediction, the interactions of protein-protein interactions, basically. So Anton, thank you very much for being here. I'm looking forward to hear your lecture. Thanks. Floor is yours.
Thank you very much, Attila, for your really very nice introduction. It has been a long time since I touched the GROMACS code, but if I get a chance, I still run the occasional MD simulation. And I would also like to thank the organization for giving me the opportunity to present some of our work here. And I have to start the screen share now, just a second. That should be this one, and then I say share, and then you should be able to see me, and then I have to find back the window where I can see people. So I'm right now I'm only seeing myself, and I'm used to people.
I see your screen.
Yeah, you see my screen. But I just wanted to say I am used to seeing. I'm used to talking in front of an audience and seeing people. So if like a handful of people wouldn't mind to turn on their camera, then I have a little bit of a feeling that I'm speaking to an audience and not just to my computer screen at home. Oh, wonderful! Thank you. Let me get you guys into gallery view. Yes. Okay, that's really nice. Okay, so it's a really nice symposium, and yeah, let's get going. I'm a little bit nervous, but that's also because you have a very nice lineup of keynote speakers. I'm in the middle between Alexandre Bonvin and Chris Oostenbrink, both of whom I know very well, and they worked in Switzerland for a long time, where they've learned to be very precise with their timing of presentations, and I don't have that skill. So I hope I'll not run over time, but I have been practicing, so I should be better at this than I used to. Okay. So today I will be talking to you about a few methods that we developed to predict the binding interface of protein-protein interactions from sequence. So this is really the bioinformatics point of view, and we're going to look at two types of interactions: between two regular proteins, where we try to predict where protein A might be interacting with protein B, and then we also have a special kind of protein-protein interactions where the other protein is actually an antibody, and then the binding site is referred to as an epitope. So we'll look at these two cases. We have two methods. One is called SeRenDIP, sequence-based prediction of interaction for proteins, and the other one is SeRenDIP CE, which stands for conformational epitopes. A lot of this stuff is published. I have some teasers at the end for some results that are not yet published, but are on their way. So look out for the links at the bottom of the screen. Then you'll find some nice things there. I hope that you find them nice. Okay, so before I go into the work, I want to say I've not done this work alone. I first want to acknowledge Jaap Heringa for being my boss in the lab for the last more than 15 years. And a lot of people during that time who have been collaborating with me, foremost Qingzhen Hao, Chinese, he's from China. He was my PhD student for about 5 years. He's now back in China. I'm still collaborating with him at the Shandong University, and he's done most of the work that I will be presenting, and most of the other people are students, master students, the occasional bachelor student, and a few other PhD students, most notably Bas Stringer and Kati Wauri, who have been also collaborating in this work. And I think that's enough for now. Okay, so first of all, why are we interested in protein-protein interactions? And maybe this is obvious for some of you, but probably not to all of you. Although I don't remember, was Alexandre Bonvin's talk before me, or is he coming later?
Yeah, he was before you around.
Was this morning, right? So then you have already had a taste of protein-protein interactions. But just briefly, my view on this is an image that I think tells the story very graphically. I like graphical explanations. This is basically an artist's representation, more or less, of a vesicle. So this is like a tiny part of the tip of a neuron. It was published in 2014 by Wilhelm et al. It appeared in the Dutch national newspapers, and it's not just an artist's impression, it's a well-informed one. So what they've done is they took a lot of proteins for which they can actually identify the quantity of them in the in this synaptic bud, and a rough estimate of their location from cryo-EM microscopy. And so this looks really realistic. But the problem is that it's not complete, and the major missing part is that, so if you imagine that this is like a car, then all the parts are there. You could build a car out of this, but none of them are assembled. So all the motor compartment, all the parts of the engine are in the engine compartment, and all the parts for the chairs are in the passenger compartment. But they're all loose parts. They're not assembled. We don't know how they're interacting. So that's why I look at protein-protein interactions, because we know a lot about the proteins, the quantities, when they're there or when they're not there in a cell at a particular state. But we also need to know which protein is working together, which other protein at which moment. So that's one of the things I'm trying to work out. And it also helps a lot in, for example, looking at sequencing data and trying to interpret why a certain SNP might be disease-causing or not, because it might not have any influence on the protein itself, but it might influence its binding to other proteins. And this is also very important for understanding how viruses work, and I don't have to spend much time in these times to explain to you what the importance is of understanding how new viruses work. And why conformational epitopes? Well, the bridge from viruses to antibodies and vaccine development is very brief. So I'll leave it at that. There are more applications, but we all know that antibodies are important. So now then the final step, and this is particularly important coming after Alexandre's talk. Why sequence-based? Because there's so many methods that use structure. There's so many structures available. Why not use them? Well, obviously, if you have a structure, you use that. But we don't always have a structure. We don't always have an experimental structure, either from crystallography or cryo-EM or NMR. And we can predict structures with increasing accuracy. AlphaFold is one of the most famous examples there, particularly actually AlphaFold 2. And they now have a database where the whole human proteome structures, predicted structures are collected, and they're working on other organisms as well. So this is impressive. There's still a fraction of the proteome that's not covered. And but also for the proteins that are covered, not all residues are actually predicted. So some parts of proteins are missing. It's still expensive for a new protein to do a prediction. It's not available for all organisms. And we also know one of the weaknesses is that when there's no homologous sequences available, then AlphaFold doesn't work very well. And we also don't know very well which other weak points AlphaFold might have, because the evaluation of the accuracy of the different predictions for types of proteins for which we don't have structures, experimental structures to compare with, we don't know how good they are. They could be very good, They could be very poor. They're probably somewhere in the middle with a wide spread. Okay, now, and particularly for interface prediction, it's not clear how helpful predicted structures might be, how accurate a prediction should be before it actually has any positive influence in predicting the interface. Maybe you need a very accurate structure before you can start to get the interface right. People are looking at this, but we don't have a clear picture there yet either. So altogether, I think there's a niche there to have sequence-based methods that try to go from a sequence patterns to the likely location of the interface directly. Not because it's the best thing to do, but before you have a structure or before you have a good enough structure, it's the first thing you can do, and it can get you started while you're working on the structure. Okay, now, just to get your minds clear about what we're meaning with protein interactions, so we're actually looking at the physical interactions of two protein molecules, making physical contact, binding to each other. And there's three types I want to discuss today. You can probably identify more if you look carefully. Protein A can bind with a different kind of protein, AB. That's a heteromeric interaction. Some proteins bind to themselves, obviously not to the same molecule, but an identical copy of the same type of protein, where A binds to A. That's a homomeric interaction. And then when a special case actually of the heteromeric interactions is where the other protein is an antibody, and then we're talking about the epitope binding or the antibody antigen binding. So in this case, the protein A is called antigen in some cases. I'll just call it protein in this lecture. Okay, so now we have the scenery set. How do we do sequence-based prediction? This is sort of the general idea. We have a sequence, maybe we collect some homologues using BLAST, and then we predict which residues are going to be on the interface. This is a little bit misleading picture. The residues are here drawn on the structure, but we don't necessarily know the structure. The residues are actually in the sequence, right? So we're going to predict that residue 60 might be on the interface, and then 122, 123, and 124 may be on the interface, and maybe 246 might also be on the interface. So there's lots of methods actually that do this. The most recent ones are similar to structure prediction methods that use alignments and look for correlations between alignment columns in the alignment of two different proteins, and then that tells you something about where the interactions might be. I'm not going to talk about that. I want to keep it simpler. Protein-protein docking, I don't have to explain. That's another method. It can be very accurate, but it's relatively slow. If it works, you get a lot more detail on the interaction than what you can get from the sequence. But because you actually get the complex of how protein A and B are bound together, so you can identify which residues from B interact with A and so on. I got the color switched around, the labeling switched around here. I don't know why. And then the third one, which is close to my heart, but way too expensive in this field. Where is it? Oh, yes. Oh, okay. Now some magic of open office here. Even slower is when you really want to have more detail on not just where the interaction happens, but also how it happens, and maybe something about the binding strength. Then docking methods are not always good enough, although also Alexandre has done some very fabulous work on estimating binding strength for protein-protein interactions. If you want to go any further, and Chris Oostenbrink actually knows way more about this than I do, then you can start doing MD simulations to calculate the binding strength. So you don't only get a lot of detail of the where the interaction happens, but also how it happens and the strength of the interaction, and maybe even which residues are contributing most to the strength of the binding. Okay, we're not going to do any of that in this talk. We're going to stick with sequence-based methods. So we're going to build a machine learning classifier to go from sequence to a prediction of the interface places. Now, for a classifier, you need two main things. You need features, that's basically the input data, and you need a data set on which you can train and test your method. And there's a lot of work behind this. You can look that up. This is work from our group. This is work from other people that we have been able to use to good advantage in this work. Now, a couple of features that we use. One is conservation. So you look in your alignment column whether the serine or so in your query sequence is also a serine in all the homologues. It might be very conserved and it's always a serine, or it might be something different in some proteins and then it's less conserved. And this has important information, which I can give a lecture about, but not today. Okay, then solvent accessibility and secondary structure are also known to be strongly correlated with interface regions. Obviously, you can get that from the structure if you have it, but we have used a method called NetSurfP by Peterson et al. That can predict this to a fairly high accuracy from the sequence. So we can actually predict these things from the sequence. And then there's a method from the group of Wim Franke in Brussels. It's called Dynamine that predicts backbone flexibility or backbone dynamics from sequence. We also use that. And then the last feature that we added is protein length, which some people, particularly machine learning people, find a really weird one, because obviously these things are all different for different locations in your protein sequence. But protein length is just one number for the whole sequence. I'll show you that it helps. And at the end, if I don't forget, otherwise you should ask me, I'll tell you why I think it's important. Okay, so that's the features. Oh yes, and then this is a general thing that most sequence-based methods use. You don't just look at one residue. You look at a flanking set of residues, in this case, 4 before and 4 after. So you have 9 residues, 9 windows in a row for which you collect all the feature data to predict whether the central residue might be on the interface or is likely not to be on the interface. Okay, now that's the features. And then the data sets, we have 3 data sets. One that we derived from the SubDOP database that the people in Oxford, in the Oxford Bioinformatics, Protein Bioinformatics group made. It's called SubDOP, so that's data of proteins bound to antibodies. This is a very misleading picture because this is not how an antibody binds, but it looks nicer. And then we have a set of homodimer complexes that we used in an earlier paper where protein A binds with protein A, and it's not showing well, but you see that this is an interface and that they have the same color. And then we have another data set of heteromeric interactions that we actually used before, but it's also derived from earlier work by Murakami and Michiguchi, who also developed a method for doing this on that same data set. Yeah, I think that's enough for now. Let me see if I can get the figures to show better. No, they don't want to show. Okay. Okay, yeah. So 3 data sets and a lot of features. So the other important thing that we do with our features is try to use them to encode evolutionary information about our protein. So evolutionary information tells you. So I mentioned sequence conservation. A serine might be always a serine at this position in your protein, but you can do the same for the features. So an alpha helix somewhere, maybe, I don't know, from 30 to 60 might actually always be an alpha helix in all the homologous proteins. Or it just happens to be an alpha helix in our query protein, but it's typically a beta sheet. So these kind of variations and patterns in those variations are very important for deciphering where an interface might be. So what we do is, well, we collect homologues just using SciBlast. We line them using muscle, both just because they're the fastest methods available. They're good enough for this purpose. And then for each of our homologues, we calculate the feature values. So the secondary structure predicted by NetSurfP, and the solvent accessibility, and the backbone flexibility by Dynamine. And we collect the value for these features from the query sequence, but also the average and the standard deviation across the homologs. So we get a sort of a typical value of like, oh, this is like 85% alpha helix with some variation, things like that. So what is the typical value of a feature at that position, and what's the variability? So some features might be conserved, so the variability is low, and others might be not conserved, and then the variability is high. Okay, so this all adds up to 172 features, because we also have 9 residue windows, so it's times 9, and then plus 1 because we have the protein length, which is just one number. Okay. This goes into our method. We use a random forest classifier. I'm not going to explain any of the details of that one because it's fairly straightforward. It's one of the most simple machine learning methods that work well on protein sequence data, and that's exactly why we used it. It's the simplest one. At the end, I'll tell you of some more advanced methods that we've used. Am I already running out of time?
You're the last speaker, so you can use until tomorrow morning, no problem.
Okay, I'll try not to do that. Okay, but I do think I have to speed up a little bit. So let's see. So I'm just want to show you here what the features do by themselves. So if you know your ROC plots, then you know 0.5 is the random value that you get in the area under the curve of a ROC plot. So these are by themselves, these features are random. If you add a few more, then you're starting to get a little bit higher, still not spectacular. If you combine them and you add a window, then you're at 0.6, which is sort of not good, but it's also not random anymore. And then if you add solvent accessibility and some more, then you can get almost to 0.7. Now, 0.7 starts to be sort of medium good. So what can we do next? Well, I have lost the windows here, so we can add the windows back in, and then we can also do some tricks with our training, with our training and validation sets, and then we actually get an accuracy of. And then this was on the validation set. This is on the independent test set. We've got an accuracy of 0.72 on the area under the curve under the ROC plot. Okay. And then there's some other metrics that we can look at, but we're not going to do that now. So how good is this? Well, this was work that we did a couple of years ago. We compared to 2 sequence-based methods. A lot of protein interface prediction methods say they are sequence-based, but they use DCSP, so the secondary structure derived from the crystal structure of the protein, which I think is not sequence-based, it's structure-based. These were the only 2 sequence-based methods that we could find, and we can see that this actually they score lower than we do on this data set. This is homomeric interactions. These other methods were meant for heteromeric interactions, so we also tested on heteromeric proteins. We do a little bit less well there, and they do a little bit better here, but we're still a little bit better than they were. We couldn't test the other method because the data set was too big. So now this led us to the idea to actually train one predictor, one predictor on both homomeric and heteromeric interactions, and we can get actually the same accuracy there. Okay. And then, okay, right. So, oh yes, and then you see here that for the, sorry, I was going too fast. For the homomeric interactions, the predictions are actually easier than for the heteromeric interactions because you see the values are lower in this case. So apparently, and I still don't know exactly why, heteromeric interactions are harder to predict than homomeric interactions, but we can actually train one predictor that can do both of them pretty well. But if you know you're looking for heteromeric interactions, then you want to use the heteromeric trained predictor, because that's a little bit better, 0.65, than the combined one that does here. But if you're not sure, or if you're looking for homomeric interactions, you might as well use the combined one, because it's the best one here on this data set. It always also depends a little bit on your data set. If you test this on a different data set, you might actually get a different performance. Okay, now what we also did, because the random forest, as I said, is one of the simplest methods, we tested a number of different deep neural net methods, particularly dilated convolutional nets, and also an ensemble method that takes this one plus 5 other types of architectures that I don't want to go into right now, and trains it on basically the same data set, or on a larger data set, or on a data set that was, oh, I should have put the reference here to Zhang and Kurgan. They made this very nice benchmark paper where they compare a lot of these methods together. So we also took their data set to train on, test on. Now, to test on. So you can see here 2 effects. So the random forest does okay, but the deeper models actually are able to capture more of the patterns from the data and get better predictions, also on different data sets. For some reasons that we don't understand yet, this data set appears to be harder than this data set. But you also see that if we train on 4,000 proteins instead of 400, then we can actually get more, apparently learn more or better patterns out of the data and get a higher accuracy here. If you compare this one to that one, then you see that there's still quite an improvement in the performance there, in the prediction. Okay, so this is one direction to improve things. And if you're interested, there's a preprint of the bioarchive under this link that you can look up all the details. It's currently under review. And another way to improve these things is to train not just on protein interactions, but train on other related tasks. And so now we're actually, so previously we took these features, buried, like this, buried, solvent accessibility and secondary structure, we took them as input from another method. Here we take them as training tasks. So we train our model. This is also a neural net model, quite a complicated one, on a number of different tasks, and the interface, protein interaction interface prediction is one of them. And then you can see if every 2-letter acronym is one task. If you train on multiple tasks, 1, 2, 3, 4 tasks, you can actually get a better performance on the protein interaction prediction. So the protein interaction, which is one of the tasks, actually gets better when you force your model to train multiple tasks. And the reason for this is that these deep learning models, they can actually capture a lot of data, but they need some guidance to understand what is the important part. And the harder you make the task, and having a combined task makes it even harder, the more patterns this model has to learn to actually be able to get good predictions. So you give the model more chance to learn more things. So that's multitask training, and and we have a lot of protein structure. We have even more protein sequence data. We have a lot of protein structure data that we don't have interface data for, right? So but for all these protein structures, we actually do have the solvent accessibility, and we know which residues are buried, and we know the secondary structure. So we can train on this and then predict that better. And you can see that here. So here you can actually see 3 things. So here we're only training on protein interactions. Here we're training with the protein interactions together. So that's multitask. And here we're training at the same time also on a lot of proteins for which we don't know the interaction, but we only know the related tasks. So the secondary structure and buried and so on. And that final one is, and the accuracy here is only on the interface prediction. So if you add more proteins in your training set for which you don't know the interface, you don't know where the interaction interface happens, but you do know the other ones, you're still improving. And to highlight where that, how big that improvement is, if you reduce the amount of protein interaction data that you use, so you throw away half, or you throw away 90%, or you throw away almost everything. So you can see that this is the performance that you get with only training on the interface data. If we combine the stuff and train on the proteins for which we don't know the interface, we only need 1 out of 8, so as much data as we used to need for the protein interactions. This is important because there are a lot of things where we have even less data than we have protein interactions for, and we would still like to be able to predict those. So this gives you a fighting chance of getting a deep learning model to do that, even though you don't have a lot of the important the features of interest annotated on your data, but you do have a lot of other data for which you have related annotations. Okay, now, then a final thing is that, we have a side step here. So you can use structure, and this is just to show you that there's one method that's called APBioNet. It's apparently the best one out there currently. This paper was from this year. So I'm thinking this is the best method right now. So we get an AUC of 0.75, and they get an AUC of 0.77. One caveat, they weren't tested on the same data set. We want to do that. We haven't had time yet. So this is a surprisingly small gap. If you look at some of the other measures, the gap is a bit bigger, but it isn't as big as you might think. So we can actually do quite well these predictions from sequence with no knowledge of the structure, and compared to when you actually do know the structure. Okay. Another thing that we do to improve, so I just told you we have a lot more structures for which we don't have the interface, but we have even more sequences for which we don't have the structure yet. And this method, where this manuscript, and this is actually already on bioRxiv since yesterday, we actually try to also train on the unannotated sequence data where we don't have any structures. So I'm not going to explain too much about this, just to tell you that this works in principle. The problem with this is that these models are extremely expensive to train, and we have a limited, not like Google was using similar models for their AlphaFold. They have basically unlimited CPU power, or GPU power, even more importantly. We don't. So we couldn't take this as far as we would have liked to, but we do show that we actually get a lot of improvement when you don't first train on the sequence data. And if you do, you can see the jump in performance. Okay. Now that was all protein interactions. I want to spell out a few words. Do I have time for a few words on the epitopes? I see people nodding. Thank you. Then so now we have these models for protein interactions. Can we use them then to predict the epitope region? And I've seen some papers where people actually try to do that. We also do this here. And so we take the heteromeric trained random forest model, and we predict on the subtop epitope data set, and then see whether the predicted interface is actually corresponds to the epitope regions of where the antibodies bind. And we get an area under the curve of 0.67-ish. So, okay, but not too good. So the next thing is then, well, maybe we just retrain the random forest model on the epitope data and it gets better. So if we do that, indeed, it actually does get better. So we can train on the epitope data, we get closer to 0.7. Now, because we already previously started training models on combined data sets, we also did that here. So now we train on the epitope data and the heteromeric PPI data, and it gets even better. So why this is, it's not so clear, because, I mean, apparently epitopes are different than heteromeric interactions. So why adding them is better? And we think it's simply just because the learning of the model is still limited by the amount of data. So it would be better to have way more epitope annotated proteins, but we don't have them. And this isn't the best thing to do, but it's the best thing we have. So more data here is the advantage. And yes, the pattern will probably be slightly different, but still it improves the prediction. If you add even more data for the homomeric interactions, actually, these are apparently, for reasons that we still don't understand yet, slightly different patterns in the sequences, then it gets worse, right? So more data isn't always the best solution. In this case, it's apparently too different, and the performance goes down. Now, I can show the same stuff in a ROC plot, and then I've actually shown some of the other methods to try to predict antigen binding regions, or the epitope regions from sequence without using structure. There are a lot more methods that also use structure here for the epitopes. It's clear to see these are our two methods, and that's the rest way down below. And you can show the same in. These were actually tested on the same data set. You can also show this in a precision recall plot, and it basically shows the same. Okay, now why these models work, and these are all our features, 172 of them, and you can calculate something that's called feature importance, and then we sort them on the feature importance of the epitope model, and then you can see that these patterns are slightly different for the other models. So these are the two epitope models, and these are the three PPI models, and you see different. So red is the most important features, and you see that there's some red ones down here that are red for the PPI, but they're green for the, so less important for the epitope. Length is at the top. Then there's a block of sequence solvent accessibility, which is no surprise because all the interactions happen on the surface, right? So knowing what is on the surface is obviously very important. Then there's a few bits of sequence conservation, and then we see a propensity for coil, which is really important for the epitopes and really not important for the protein-protein interactions. So these are the most striking things that we saw in the differences in the features. We can dive a little bit deeper into that if we would have had the time today, but we don't. I just want to tell you here that if you, just one thing here, if you remove length, so one feature out of 172, just one, your AUC of your ROC plot drops from 0.79 to 0.63. This is a huge drop. So even though length doesn't tell you anything specific about whether this residue is different from that one, because the length of the protein is the same for all of them. What it does tell you is the size of the protein. And an interface doesn't vary in size that much. They're roughly the same size. Proteins can be very large or very small. And a small protein, therefore, has a relatively large interface because the interface is the same size. So for a small protein, you need to predict more residues as interface, relatively, than for a big protein. Right. So if an interface on average is 10 residues, then for 100 residue protein, it's 10% of your protein. But for 1,000 residue protein, it's only 1%. Yeah. So we think that length allows the model to sort of make this normalization and improve the prediction there that way. Now, also for structural, epitope prediction, there's methods that use structure, as I already mentioned. And the difference here is way, way smaller than for the protein interactions. Why this is, I don't know. Maybe it's easier to predict them from sequence. Maybe the methods for structure-based epitope prediction aren't as well developed as they are for protein-protein interaction prediction. I don't know. This is something we want to look into, but we don't have the answers there yet. Okay. Yes, this is the unavoidable one to show. This is the epitope predictions that we do for one of the SARS-CoV-2 proteins. It's the receptor binding domain of the spike protein, if I'm not mistaken. If you want to look up the PDB ID, it's this one, and this is the binding region of the epitope of the antibody that's present in this PDB structure. And you can see here in the structure, but also down here in the sequence, that a lot of the predicted residues are actually at the same position as the binding region of the antibody in structure. Now, that was it. Yes. So just as a summary, so we're predicting interface from sequence. We use evolutionary context from the multiple sequence alignment. We also have a web server if you want to try it out. It's not super fast because for each of the homologues we have to calculate these features, and that's not expensive for one protein, but you can have like up to 500 homologues, and if they all take 1 minute, that's a little bit expensive. There's different predictors for pre-PI, for combined or only heteromeric, and then for epitopes. So you have to select the right one. So we seem to be better than the other sequence-only predictors, and the gap with structure-based predictions is not as bad and not as big as you might expect. And that's it for me for today. So I'm happy to take any questions. I see some in the chat.
Anton, first let me say thank you for this great and very energetic presentation, especially boosted our energies as the last presentation here, so we can go away with a lot of power. So thank you for that. So I see indeed two questions there. One is from Montesir Alam. He says, you mentioned that there are occasions where we can't trust the 3D structure at hand. How does it compare with the uncertainty associated with sequence data?
I'm not sure what you mean. Well, first of all, thank you for the question, but I'm not so sure what is meant with the. So maybe Montasir, if I pronounce your first name correctly, if you could turn on your microphone, or because I'm not sure what you mean with uncertainty in the sequence data. The protein sequence data is fairly accurate. I mean, there's some error rate in the sequencing. But I don't think that is what you mean. So I'm not sure how to answer your question. I'm sorry.
Yes, Dr. Feenstra.
Yeah.
I was just thinking that there are some uncertainty associated with the sequence data, and there are some uncertainty that is associated with the information that captures the 3D structure. So I was just trying to compare that with the accuracy by which we know the 3D structure can be compared with the sequence data accuracy.
Okay, well, I find this a very difficult question to answer, mostly because I haven't thought about it a lot myself. So as I said, the sequence data is fairly sort of cast iron. This is the protein sequence. We know it is there. There are some caveats there because you don't always necessarily know which splice form, for example, is the dominant one for the protein in a cell. If we're talking about eukaryotes, there can be that's not really sequence based, but there's often post-translational modifications that are involved in the protein interaction. Obviously, we don't know them if we only have the sequence information. Of course, there's methods to predict that, but that's a different topic. For structure data, there are more sources of error or uncertainty. First of all, structures are typically either cryo X-ray or cryo-EM, so low temperature frozen samples, and the structure that the protein has there might just not reflect what the dominant structure is of the protein in a cell. Likewise, for the protein interactions that we use the annotations for to train on, the actual bound structure of the crystal, the two proteins in the crystal structure might just be different from how they bind precisely in the in the solvent. There's a different kind of uncertainty, that there's lots of proteins for which we don't know whether they have a defined structure all the time. Disordered proteins particularly, or proteins with disordered regions, typically larger loops. Incidentally, the antibody binding site, so the paratope that binds the epitope region of the protein that the antibody binds to, typically also consists of loops that are typically unstructured when they're not bound to the target protein. And likewise, a lot of proteins, only non-antigen protein, non-antibody proteins, also have floppy loops that are part of the protein interaction, but only become structured when they interact with the target protein. Does that answer your question?
Yes, yes. Thank you very much. I was actually thinking about more. I was actually thinking more about quantifying the uncertainty associated with the data, but yeah, I'm satisfied with that. So thank you very much.
Yeah, we are actually diving back into the annotations and how we derive them from. There's the PDB, there's a subtop that I already mentioned. There's the PISA database that tries to annotate protein interface regions from the structure. And one of the things I haven't mentioned is crystal contexts. So sometimes it's difficult to see the difference between a protein interaction and the crystal contact in the crystal. So we're actually now trying to look into this type of uncertainty and whether how much it matters on which type of data or which subset of the data we train our method. So this is ongoing work, and if that goes as I hope, then we should have a paper on that somewhere next year.
Okay, thank you, Montesir, for your question. And I think the final question is from Alperen Taciroğlu. He says, is there a commonality within interaction data sets where accuracy is lower than the rest? Anton?
Okay, so I think you mean, are there certain types of proteins where the prediction is less accurate than other types of proteins? So as far as we have looked at this a little bit. We have a few things that we did is, so maybe we're better at predicting well for big proteins, or maybe we're worse at predicting well for big proteins. So we sorted our data set or test set on protein length, and then you can look at the area under the curve for long proteins. So this is long proteins and this is short proteins, if I remember correctly. No, this is short. This is long proteins. You see that there is a slight trend here. So it appears that for the shorter proteins, we're slightly better at predicting than for the longer ones. Somebody has discovered the annotation feature of Zoom. So that's one of the things we did. What we also did is slightly differently. So we looked at the size of the annotated interface, and so it's not true that, so if the interface is small, it's not true that if the interface is small our predictions are bad, but the worst predictions, so low area under the curve here, are all for small interfaces. Now this can have lots of reasons. Maybe they have slightly different patterns, maybe there's just not enough data there in this database to make a good assessment of the accuracy or to train on. But we think that what also might play a role here is that if these interfaces are small, maybe this is not all the binding regions that this protein has. Maybe it's just one protein that happens to bind here, but there could be other proteins binding on different places. So this could also be an under annotation. So missing annotations, basically, so things that we predict as interface, which are now counted wrong as being wrong, but they might actually be an interface, but we don't have the crystal structure that actually proves that this is the case. So this is one thing. There was also, I don't have the plot here. We also looked at whether, so we mapped our predictions back onto PFAM and or SCOP, I think, protein families. to look at whether there are particular protein families for which we did particularly well or particularly poorly. We didn't see a strong pattern there. We also looked separately at proteins with disordered regions or transmembrane proteins, and there was no significant difference in accuracy between those subsets. But we only have a few of those in our data set, obviously because, well, disordered proteins won't crystallize, and also transmembrane proteins are very hard to crystallize and obtain structure of. Okay.
Okay, thank you, Anton. There is, I just see a new question popping up. Marie-Jo.
More of a suggestion, if I read it correctly, to discuss whether a neural network or a decision tree might be a good model for training these or for basing these predictor methods on. Yes, I think that's a very okay. Oh, you're asking for my advice. Okay, so generally take the simplest one first. Because certainly if you're new in the field, then if you're new to machine learning methods, for sure, take the simplest model, random forest models. There's also decision trees, which are even simpler. There's just one tree out of the forest, so to say. There's not much. There's a few things you can do wrong. There's far fewer things you can get wrong with random forest models than with even simple neural net models, in terms of training, in terms of testing them properly, in terms of avoiding overtraining. And if it gives good enough performance, then you're done. You don't need a more complicated model if your performance is good enough. You also need a lot more data to train these more complex models well enough, and also to have sufficient independent test data to test whether you haven't been overtraining on your training set. Is that enough to get you going, Marie? I'm assuming. Details were in the conference website, I see. So if you have further questions on this, please feel free to contact me. One of the nice things about doing this conference maybe one of the fewer nice things of doing it online instead of in a real audience is that in this case I can actually address people by their name. Because in reality, I would probably only see a face and I wouldn't know what name goes with it.
Yeah, that's true. So, Anton,
Attila, could I ask one?
Yeah, sure.
Yeah. Thank you, Prof. Anton, for the wonderful presentation. Unfortunately, I missed bits and pieces, so I'm going to ask a question where if you have already addressed it, do feel free to ignore it. But it's more of a mixed bag. So, if I understood correctly, you're looking at epitope prediction using protein interaction data, and it's coming pretty close to the structure-based methods, which is great. Now, structure-based methods themselves are not really up there in terms of the desired kind of accuracy that we want. So, what do you think is really left behind? What are we really waiting for to be able to take the accuracy of structure-based prediction to the desired level, which we see with T-cell epitope prediction? I mean, those are pretty much up there. What is missing? And have you explored? Already done combining your approach with the structure-based approach, and would that take it much higher? I'm not sure. Maybe you already addressed that. So yeah, those two questions.
I have not addressed that. A very, very good, very interesting question. Thank you. So, but it's a complicated one, so I'm not sure where to start. Let's start with the easy part. I don't know. I'm not sure why these structure-based methods aren't. Let's just show that slide again, right? This is the area under the curve for structure-based epitope prediction, and it's at the area under. It's even lower than some of our models. This is just weird, right? Why isn't it a lot better? Okay, so the F1 score here is much better than ours, or it's actually a bit better. If you look at the PPI prediction, the structure-based methods are. Where do I have that slide? Where is it? the structure-based methods are actually way up there. Maybe not as accurate as you would hope, but this is accurate enough to be useful for a lot of applications. I'm not sure. One of the things that we're exploring at the moment is whether there isn't something weird about antibodies. And antibodies are, for sure, they're different. We've also seen that because if we train two different classifiers, a special classifier for the epitope prediction is better than the PPI predictor for epitope recognition. But the antibodies have a very different background than evolved binding partners. Evolved binding partners have millions or even billions of years of shared evolutionary history. Antibodies are a sort of a rapid response to a protein that you haven't seen before. So it can't have the same sort of specificity of binding because that just takes more time to refine all the interactions. So that's just sort of my hunch for why they're different. It's very hard to come up with a way to actually test that. We can't wind back evolution a billion years and then change something and see how it would end up if you try it again. So I'm thinking of ways to test this, but I don't have a set plan at the moment. But it is something I'm very much interested in to understand where the apparent limits of these methods come from.
Thank you.
One of the things that we we have started trying now, so we're extending this multitask learning strategy. Giving this talk, it's the obvious next thing to do, right? So we predict secondary structure, solvent accessibility, buried exposed, protein-protein interactions. So what's the next track we're going to add? It's epitope interactions, right? So we're going to add them as a fifth task into the prediction task. We have a lot more PPI data than we have epitope annotations, so we hope that this would actually these results might actually give us some clue about why they're different or how they're different. But we still have to see what comes out of that. That project was just started like last month, so I don't even have any preliminary results from that to share with you yet. Thank you for the question. Yeah.
Anton, thanks. If you have still energy, I see another question from Jaap Flowhill.
Yeah. No, we haven't done that. Very intriguing idea. Jaap, if you have the sequence of them, I know I could probably get it, but feel free to run it on our web server and see what comes out of it, and let me know, because I'm curious as well. We're really trying to focus on the method development because that's already really takes a lot of time. We didn't have much time to try out interesting new applications, but this is certainly a good one. Okay, thank you very much.
Thank you very much. I don't see any more questions. If they come up, I will mail them to you and then share answers with the audience. Thank you again. We were very lucky having you here. We had also Chris and Alexandre Bonvin this day, so we had a very strong lineup with very good keynote speakers. Thanks again for being here, and I leave the floor to Nihan.
Yeah, thank you very much.
So thank you, Dr. Anton. It was a pleasure listening to you. I hope our participants have enjoyed as much as I did. I would like to thank Professor Attila for being such an excellent chair of the sessions. This brings us to end of the day one. We will release the feedback form for the day on chat. Please kindly fill up the forms. Before leaving, I would like to remind our participants to check our website for the program and also refer to their emails to which we have sent the program details. If you have any questions, please drop us a message on Discord channel or send us an email. We take leave now. Have a great evening ahead and see you tomorrow.
Anton, dankjewel.
Ja, dankjewel Attila.
Het was fantastisch om jullie alle drie hier te zien vandaag op een afstand natuurlijk. Maar we begonnen met Chris, daarna Alexandre. Hem ken ik natuurlijk niet persoonlijk, maar via zijn publicaties. Dus het was fantastisch om jullie beiden hier te zien. Dank voor dit.
Ja, heel graag gedaan. Het was erg leuk om te doen. Leuker dan ik van tevoren had gedacht. Want het is altijd heel erg afwachten hoe dat werkt online. Of je een beetje een gevoel van interactie kunt krijgen. En dat lukt best aardig, gelukkig.
Ja. Voor ons is het natuurlijk een buitenkans. Je weet dat het economisch hier minder goed gaat. En ook in Azië gaat het niet zo heel goed. We hebben heel veel mensen uit India en Indonesië. En een online meeting dat ook nog gratis is natuurlijk heel erg goed toegankelijk. En deze meeting heeft ervoor gezorgd dat belangrijke informatie voor hun voeten werd neergelegd. En dat is fantastisch. En daarvoor mijn dank.
Ja, graag gedaan. Ik vond het erg leuk om te doen. Dus voor jullie natuurlijk ook een leuk stukje promotie om jezelf op de kaart te zetten. En voor mij ook, voor mijn eigen werk. Echt een preprint die ik echt letterlijk gisteren nog gauw eventjes naar BioArchive heb gestuurd. Van jongens, ik wil een link op mijn slides hebben. Mag dat? Ja, is goed. Oké. Ja, dus erg leuk.
Oké, ik heb de recordings even dicht gegooid.
Je kunt er altijd nog stukjes afknippen, hè?
Ja, ik zal het zo zeggen. Ja. Ik hoop je nog eens snel te zien. Ja?
Ja, zeker.
Oké.
En nogmaals heel erg bedankt voor de uitnodiging. En hopelijk ook tot binnenkort. Als jullie nog eens een keer iets